What if everything we know about history is just the final act of a much older play? Across the endless cycles of time, empires rise and fall, continents drift, oceans expand and retreat, and mountains crumble into dust. We think of ourselves, Homo sapiens, as the pinnacle of intelligence, the first sentient species to gaze up at the stars and wonder. But what if we're wrong? What if we're merely the latest in a long line of civilizations that bloomed and vanished long before our first ancestor ever walked upright? This is not the opening to a science fiction story. It's a legitimate scientific question posed by real researchers, peering into the immense darkness of deep time. Time so vast, so unfathomably long, that even imagining it challenges the limits of our comprehension. Earth has existed for over 4.5 billion years. In that incomprehensibly long span, human history, everything from the invention of fire to the internet, occupies just a flicker, a microscopic sliver of time barely visible on the geological calendar. Now imagine this. Buried somewhere deep beneath the layers of rock and silt, beneath miles of shifting tectonic plates and oceans of sediment, there may lie the ghostly remnants of an earlier intelligent species. One that, like us, built cities, harnessed energy, shaped the world around it, and then disappeared. Maybe it vanished in a global cataclysm. Maybe it destroyed itself. Or maybe it left intentionally. And if such a species once existed, what traces would it leave behind? Could we even recognize them after millions of years of geological activity? Could signs of their presence be hiding in plain sight, scratched into stone, encoded into the DNA of life, or suspended in layers of strange chemical residue? This idea is haunting not just because it challenges the uniqueness of humanity, but because it implies that history might repeat itself. That intelligence, civilization, and self-destruction might be cycles rather than singular events. That we, too, might someday be forgotten, our cities crushed to sand, our monuments buried, our satellites fallen from the sky, and our species spoken of only in the whispers of future archaeologists. This isn't merely wild speculation, it's a formal question in the field of planetary science. And it has a name, the Silurian Hypothesis. Before we venture further into the depths of this idea, it's important to frame our perspective. Our understanding of Earth's history is like a puzzle in which 99% of the pieces are missing. The deeper we go into the past, the less evidence we find, and the harder it becomes to interpret it. And yet, just as we scan the skies for signs of alien life, shouldn't we also consider looking downward, into our own Earth, for the possibility of ancient intelligence? Could there have been a time, millions of years ago, when another form of consciousness gazed across the land and called it home? Could Earth hold not just fossils of beasts and bones, but forgotten ruins of thought? This question forms the core of what we'll explore in this video essay. Not through the lens of conspiracy or fantasy, but through science, reason, and evidence, mixed with speculation that stretches the edges of the known. Because to truly understand what might have come before us, we must challenge the assumptions that define our place in the timeline of life. And in doing so, we may uncover not just a deeper history, but a glimpse of our own possible future. The idea that another civilization may have once inhabited Earth long before us moves beyond myth and speculation when examined through the lens of the Silurian Hypothesis, a scientific thought experiment first proposed by Gavin Schmidt, a climate scientist at NASA's Goddard Institute for Space Studies, and Adam Frank, an astrophysicist from the University of Rochester. These are not fringe thinkers. These are established scientists working at the intersection of planetary science, geology, and the search for life beyond Earth. They weren't trying to prove that a lost civilization existed. Rather, they asked a more profound and testable question. If an advanced civilization had arisen on Earth millions of years ago, would we be able to detect its existence today? That's the heart of the Silurian Hypothesis. It's not about aliens, or ancient astronauts, or forgotten myths. It's a serious inquiry into the limitations of geological evidence, and what traces our own modern civilization might leave behind, say, 100 million years from now. Would future beings, intelligent or not, ever know we were here? Or would time erase every trace of us? The hypothesis takes its name, interestingly enough, from an episode of the British science fiction show Doctor Who, where an ancient race of intelligent reptiles, called the Silurians, are discovered to have ruled Earth in prehistoric times, long before humans. Though not scientifically accurate in dating, the Silurian period predates dinosaurs by hundreds of millions of years. The reference was compelling enough to capture the imagination and become a useful shorthand for the hypothesis. Schmidt and Frank published their ideas in 2018 in a paper titled, "The Silurian Hypothesis: Would it be possible to detect an industrial civilization in the geological record?" The paper doesn't claim any evidence for such a civilization. It simply explores what sort of markers a technological society like ours might leave behind, and how long those markers could persist in Earth's geological layers. Think of it like this: we're living in what many scientists now call the Anthropocene, a proposed epoch defined by human activity. Our impact on the planet is immense, from widespread plastic pollution to dramatic increases in greenhouse gases, rapid species extinction, and massive land use changes. We're terraforming Earth, in a sense, even if unintentionally. So if our civilization were to vanish tomorrow, what aspects of our presence would remain detectable a million, or 10 million, or even 100 million years from now? Would skyscrapers fossilize? Probably not. Would highways, cities, books, or even bones endure? Likely not. What might survive, however, are technosignatures, indirect indicators of industrial activity. Unusual chemical isotopes, synthetic materials like plastics, and anomalies in climate records could persist for long periods. In short, the Silurian hypothesis flips the Fermi paradox inward. Instead of asking, "Where are they?" in the cosmos, it asks, "What if they were already here, and we simply can't see them?" But here's the twist: if detecting a lost civilization from 100 million years ago is nearly impossible, then how would we know if one ever existed? And what does that say about how we study not just Earth, but distant planets in our search for life? The Silurian hypothesis is not just a quirky idea, it's a sobering reminder of how easily the record of existence can vanish. It reframes our understanding of history, suggesting that the absence of evidence isn't necessarily evidence of absence. It pushes science to think not just forward in time, but backward, with the humility to recognize the limitations of our tools, our knowledge, and our assumptions. In this light, the hypothesis becomes a mirror. It asks us to consider our own legacy. What will remain of us? Will our footprint endure? Or will we too be swept away by time, as invisible to the future as any hypothetical ancestors are to us now? The name, Silurian Hypothesis, may sound like something drawn from ancient geology, but its origin is rooted more in science fiction than in stratigraphy. It's a deliberate nod to Doctor Who, the long-running British television series known for blending cosmic speculation with whimsical time travel narratives. In particular, the term refers to an episode from 1970 titled Doctor Who and the Silurians, where the Doctor encounters a race of ancient, intelligent reptiles who ruled the Earth long before humans ever existed. In the show, these so-called Silurians evolved on Earth during prehistoric times, developed advanced technology, and eventually retreated into hibernation underground to avoid a cataclysmic event they believed was imminent. Millions of years passed. The world changed. Dinosaurs came and went. Mammals emerged. And finally, humans evolved and inherited the surface, completely unaware that they might not be the first sentient masters of the planet. It's not a coincidence that Gavin Schmidt and Adam Frank chose this fictional species to name their hypothesis after. The reference was not just playful, it was strategic. It encapsulated the core idea behind their thought experiment. What if Earth had hosted a civilization long before humans, so long ago that all evidence of its existence has vanished? Now, scientifically speaking, the actual Silurian period, named in the 19th century after a Celtic tribe called the Silures, is much older than the time frame the hypothesis concerns itself with. The Silurian era lasted from around 443 to 419 million years ago, which predates dinosaurs and even the first forests. It was an age dominated by trilobites, jawless fish, and primitive coral reefs. If an intelligent species had arisen during that time, it would have been nothing short of mind-bending, a type of Earth-born alien intelligence thriving in an ecosystem we can barely comprehend. The anachronism is acknowledged by Schmidt and Frank, who admit the name isn't geologically accurate. Still, the name stuck because it achieved something deeper. It sparked curiosity. It invited the public and the scientific community alike to think in ways they hadn't before. After all, if you want to challenge entrenched assumptions, sometimes a provocative name is the perfect entry point. This fusion of scientific inquiry and cultural imagination is part of what makes the Silurian Hypothesis so compelling. It's not suggesting that the creatures from Doctor Who actually existed. Instead, it uses the story as a metaphor, a launching pad, for a very serious question. It illustrates how fiction and science often walk hand in hand, especially when trying to conceptualize phenomena far outside our everyday experience. There's also something quietly profound about the name itself. By invoking a fictional narrative in the context of scientific rigor, it challenges the boundary between what is possible and what is dismissed as fantasy. It reminds us that sometimes the outlandish ideas in fiction, like Jules Verne's submarines or Arthur C. Clarke's satellites, can inspire real-world innovation and discovery. And in this case, a decades-old TV show gave language to a question that had long gone unasked. Could we be missing entire chapters of Earth's history, not because they never happened, but because time erased every trace? So while the name might be scientifically imprecise, it captures the essence of the hypothesis perfectly: unsettling, thought-provoking, and wide open to reinterpretation. In just one word, Silurian, we are nudged to consider a version of Earth where humanity is not the original protagonist, but perhaps just the latest cast in an ancient, repeating story. To even begin evaluating whether an ancient civilization could have existed long before humans, we must first ask a foundational question: what exactly is a civilization? The word itself evokes images of grand cities, massive monuments, and sprawling empires, but beneath these visuals lies a deeper, more nuanced structure. Civilization is not merely the presence of people, it's the expression of collective intelligence shaped into systems, infrastructure, and long-term change. And to identify one, even a hypothetical one lost to deep time, we must understand the specific hallmarks that define it. At its core, a civilization requires several key components: organized social structure, technological advancement, agriculture, urbanization, and energy use. Each of these elements leaves behind, at least in theory, detectable fingerprints. And the more advanced and expansive the civilization, the more lasting those fingerprints might be. Let's begin with cities. Urbanization is a defining trait of civilization. Cities are more than dense clusters of people. They are hubs of administration, commerce, culture, and control. They require planning: roads, plumbing, storage, housing, defenses. The presence of cities implies a sophisticated level of social organization. But in geological time, even cities built of stone can vanish. Think about how many ancient human cities, only thousands of years old, have been swallowed by jungle, buried under sediment, or crumbled to dust. If this can happen in mere millennia, what would be left after tens or hundreds of millions of years? Then there are tools. The ability to create and use tools is one of the earliest signs of intelligent life. For a civilization to exist, tool use must advance beyond basic survival. It must evolve into engineering, machines, architecture, metallurgy, fabrication. The development of complex tools reflects abstract thinking, problem-solving, and cumulative knowledge passed through generations. In our own case, we've gone from stone axes to quantum processors in an evolutionary blink. But tools, especially those made of organic material or unprotected metals, degrade quickly. Unless preserved in ideal conditions, most of them would not fossilize. Even so, if an ancient civilization used synthetic materials, alloys, or ceramics, some trace might persist, hidden in mineral veins or locked inside untouched strata. Agriculture is another crucial marker. A civilization cannot survive without food surpluses, and to create those, a species must learn to control its environment. This includes cultivating crops, domesticating animals, and modifying landscapes, irrigation systems, terracing, storage silos. Agriculture reshapes ecosystems, reduces biodiversity, and alters the chemistry of soils. It's one of the few activities that leaves long-lasting environmental changes. Yet, over geologic timescales, even these changes can be overridden by the slow churn of plate tectonics, erosion, and biological recovery. Next is energy use, perhaps the most telling trait of a civilization that could echo through time. When a species begins to manipulate energy beyond its own biological metabolism, burning wood, coal, oil, splitting atoms, it alters its environment dramatically. Industrial-scale energy use generates waste products, greenhouse gases, radioactive materials, and novel compounds. These can leave chemical signatures in sediment, ice cores, and even tree rings. Our own industrial age, only 2 centuries old, has already produced noticeable atmospheric shifts, altered global temperature patterns, and filled the oceans with synthetic compounds. If another civilization did something similar, whether through fossil fuels, nuclear reactions, or unknown means, there's a chance those changes might linger deep within the geological record. In addition to these primary traits, civilizations often give rise to secondary expressions: art, language, writing, law, and economics. These are harder to detect archaeologically, especially after millions of years. Yet their effects ripple outward into the core systems, shaping construction, trade, war, migration. If evidence of these things once existed, it would have to be inferred from patterns, disruptions, and anomalies in the natural world. So, when we talk about looking for a past civilization, we're not talking about finding a complete building, an intact skeleton, or a buried spaceship. We're looking for patterns, consistent disruptions or changes in Earth's systems that might suggest something intentional once acted upon them. We're looking for ghosts in the machine of Earth's geological memory, traces of intelligence embedded not in artifacts, but in the scars left behind. The Silurian Hypothesis doesn't hinge on discovering an ancient stone tablet with inscriptions or a perfectly preserved structure from a lost world. Instead, it hinges on whether we can define the bare minimum signs of civilization, those that would stand the test of deep time, and then ask if we see anything like them buried in the vast archive of Earth's ancient rocks. And even then, we must confront the next, even harder question: would those signs still be visible after hundreds of millions of years? To truly grasp how difficult it would be to find evidence of a civilization that predates humanity by tens or hundreds of millions of years, we must understand the daunting concept of deep time. Deep time isn't just a long time, it is time on a scale so vast that it defies human intuition. We are used to thinking in terms of centuries, maybe millennia. But Earth's timeline stretches back over 4.5 billion years. That's 4,500,000,000 years, a number so huge it becomes abstract. And within this massive span, the rise and fall of entire ecosystems, species, and possibly civilizations can vanish without a trace. This is the deep time problem. Consider this: if all of Earth's history were compressed into a single calendar year, humans wouldn't appear until the very last few seconds of December 31st. Everything from the rise of agriculture to modern smartphones would fit inside a flicker of time. That means entire geological epochs have come and gone long before humans ever existed, and that's exactly what complicates the search for ancient intelligence. Our civilization, for all its advances, has only existed for around 10,000 years if we're being generous, starting with early agriculture and permanent settlements. Industrial civilization? Barely 200 years. That's an almost laughably short span when compared to the hundreds of millions of years represented in the fossil record. Even if a past intelligent species had existed for tens of thousands, or even hundreds of thousands, of years, it would still be just a speck of sand on the vast beach of Earth's history. Now ask, what happens to evidence of a civilization over that kind of timescale? The surface of the Earth is not static. It is alive with movement. Tectonic plates shift, volcanoes erupt, continents drift, and mountains rise and fall. The Earth's crust is recycled over time, pushed downward into the mantle at subduction zones and remade at mid-ocean ridges. The oldest seafloor on Earth is only about 200 million years old, because oceanic crust is constantly being destroyed and regenerated. So if a civilization existed primarily on land masses that are now deep under the ocean, or on crust that's since been subducted, all its cities, monuments, and technologies would be completely obliterated. Then there's erosion. Wind, water, and ice wear away at the surface relentlessly. Buildings collapse, are buried, crushed, and ground to dust. Forests reclaim structures. Deserts bury roads. Over time, even stone monuments degrade. Think of the Great Pyramids, still standing, yes, but already weathered after just a few thousand years. Now project that over 10 million, or 100 million years. Even the strongest structures would likely disappear unless protected under very specific geological conditions. Another challenge of deep time is sedimentation. Most of the Earth's long-term memory is stored in sedimentary rock layers, laid down in lakes, seas, and oceans over millions of years. But these records are patchy. Erosion removes layers. Tectonics twist and fold them. Some periods in Earth's history are well preserved, others are essentially missing. Scientists call this the rock record bias, the idea that some environments are much more likely to preserve evidence than others. This makes searching for signs of an ancient civilization incredibly difficult. It's like trying to piece together a 1,000-piece puzzle from just 10 random pieces, most of which are weather-worn and scattered. Even if we did find anomalies in deep layers, strange isotopic signatures, unexpected carbon levels, or unusual metal distributions, how would we know they were the result of intelligent activity rather than natural processes? Our ability to detect industrial civilization is based on our own behaviors and technologies. But an entirely different civilization might have evolved very different methods of energy use or construction, ones that leave little or no familiar residue. The deep time problem isn't just about time, it's about interpretation. It's about trying to read a book when most of the pages are gone, the ink has faded, and we don't even know what language it was written in. In short, deep time wipes the slate clean. That's the heart of the Silurian Hypothesis challenge. If an industrial civilization had existed 100 million years ago, perhaps in the Cretaceous, alongside the dinosaurs, it may have been completely erased by geological processes. We wouldn't even know what to look for. And even if we did, we might be staring directly at the evidence, and not recognize it for what it is. Our entire understanding of history is constrained by the slice of time we happen to live in. But Earth doesn't think in centuries. It thinks in eras. And when we expand our thinking to match Earth's own timeline, we open ourselves up to a haunting possibility that intelligent life may have come before us, and been lost, not in myth, but in the stone. To understand the full weight of the Silurian Hypothesis and the possibility of forgotten civilizations, we must first come to grips with just how old the Earth really is. Our planet is not ancient by human standards, it is ancient by cosmic standards. Earth formed approximately 4.54 billion years ago, born out of the remnants of a star that went supernova, seeding our solar system with the heavy elements necessary for life. Imagine that span, 4.5 billion years. Not million, billion. It's an incomprehensibly long stretch of time. To put it into perspective, if you compressed all of Earth's history into a single 24-hour day, humans would show up just a couple of seconds before midnight. In fact, all of recorded human history, everything from the pyramids to the moon landing, would occur in just the last fraction of the last second. That's how little of Earth's story we occupy. Let's zoom through the planetary timeline. The Earth cooled enough for a solid crust to form within the first few 100 million years of its existence. Then came the formation of the oceans, likely from water vapor released by volcanic outgassing and possibly supplemented by icy comets and asteroids. Life appeared surprisingly early, perhaps as early as 3.8 billion years ago. These first life forms were simple, single-celled organisms, living in oceans, thriving around hydrothermal vents or in shallow tide pools. And then, for billions of years, not much changed. From 3.8 billion to roughly 600 million years ago, Earth was dominated by microbial life. No forests. No animals. No flowers. Just microbial mats, algae, and single-celled lifeforms gradually transforming the atmosphere through photosynthesis, It wasn't until about 540 million years ago, the Cambrian explosion, that complex multicellular organisms emerged in earnest. From that point on, evolution picked up speed, and within a few 100 million years, vertebrates, insects, plants, and eventually reptiles and mammals arose. Dinosaurs dominated the Earth for over 150 million years, starting around 230 million years ago. That's an eye-opening detail. Think about it, dinosaurs were here for over 700 times longer than Homo sapiens have existed. And yet, they left no evidence of civilization, at least, not that we've found. Now consider this, humans in our modern anatomical form, Homo sapiens, have only existed for about 300,000 years. Civilization, as we understand it, began around 10,000 years ago, with the advent of agriculture in Mesopotamia. The Industrial Revolution, which launched humanity into a new era of global influence, began a mere 200 years ago. And everything we associate with modernity, from electricity and computers to global air travel and space exploration, has happened in the last century. Let that sink in. In a planetary timeline stretching across 4.5 billion years, we've been around for an infinitesimal moment. Which raises an unavoidable question: if an intelligent civilization had existed even 100 million years ago, would we recognize its remains? Or would its entire legacy be erased, compressed, subducted, and reabsorbed into the Earth's mantle, leaving no more trace than a layer of ash or an anomalous chemical signature? It's tempting to believe that we would surely know if something like that had happened. But human arrogance often gets in the way of such humility. We forget how new we are. We forget how fragile the geological record is. We forget how much time the Earth had to work with before we ever arrived. Let's go back to the calendar analogy. If Earth's history were a 365-day calendar, Homo sapiens would emerge around 11:36 p.m. on December 31st. Recorded history? Just the last 13 seconds before midnight. Everything we know, everything we've built, every discovery, every invention, all of it has occurred in less time than it takes to blink at the scale of geologic history. This perspective isn't just humbling. It's sobering. Because if intelligence like ours is possible, and we know it is, because we're here, then what's to say it didn't happen before? The Earth had billions of years to roll the evolutionary dice. What if we're not the result of a unique trajectory, but simply the most recent winners in a long game of rise and fall? After all, nature abhors permanence. Ice ages come and go. Continents drift. Oceans flood and recede. Species flourish, and then, often suddenly, they vanish. Perhaps buried somewhere deep beneath miles of crust, beyond the reach of our current tools or imagination, there lies the shadow of an ancient civilization, long erased not because it was unworthy of remembrance, but because the Earth simply moved on. When we peer back into the vast scroll of Earth's history, we don't just see a static timeline, we see an epic canvas. A billion-year blank canvas, in fact, with enormous stretches of time that are largely unaccounted for in terms of what life was doing, how it was evolving, and what, if anything, might have risen beyond basic survival to build, to shape, to leave a mark. The silence in the rock record doesn't necessarily mean nothing was happening. It could also mean we simply can't see it anymore. Let's begin with the late Paleozoic and Mesozoic eras. These are stretches of time lasting hundreds of millions of years, long before any trace of modern humans, or even mammals. During the Permian period, some 300 million years ago, life was already teeming across land and sea. Massive swamp forests covered much of the Earth's surface, and large vertebrates roamed freely. The Permian ended in catastrophe, an extinction event so massive that it wiped out over 90% of marine species and 70% of terrestrial species. But before that cataclysm, there were millions upon millions of years where the planet was relatively stable. What might have happened during that quiet time? Or consider the Jurassic and Cretaceous periods, time frames dominated by dinosaurs, yes, but also filled with evolutionary experimentation. These periods alone lasted over 130 million years. That's more than 600 times longer than all of recorded human civilization. In that time, some dinosaurs evolved feathers, bird-like lungs, and even complex social behaviors. If an intelligent species had arisen, perhaps in an isolated ecosystem like an island or a coastal region, and built a civilization during this period, it could have risen, fallen, and been erased before the asteroid struck 66 million years ago, and we would likely never know. But those are just the more well-known ages. Let's go even further back. The Devonian period, sometimes called the Age of Fishes, spanned from about 419 to 359 million years ago. It was a time when vertebrates began venturing onto land, plants colonized continents, and vast reef systems flourished in the oceans. Could intelligence have emerged in an amphibious species? Could some now forgotten branch of life have stumbled onto self-awareness and tool use, only to vanish in one of Earth's many extinction events? Even more tantalizing is the Proterozoic Eon, stretching from 2.5 billion to 541 million years ago, a time before the Cambrian explosion of visible, fossil-rich life. For nearly 2 billion years, life on Earth remained mostly microbial. But what if complexity evolved in ways we haven't imagined, forms of intelligence that weren't based on neurons or bones, but on entirely different biological systems, ones that left little or no trace in the fossil record? The problem isn't a lack of opportunity. It's quite the opposite. There have been countless windows, tens of millions, even hundreds of millions of years at a time, where intelligent life could have evolved, flourished, and disappeared. The Carboniferous period, for instance, is a striking candidate. Around 300 million years ago, oxygen levels were unusually high, reaching up to 35%, compared to today's 21%. This made insects and other arthropods grow to massive sizes, like dragonflies with wingspans of nearly a meter. But more importantly, the climate was relatively stable, and plant life abundant. Could some line of evolution during this oxygen-rich era have led to intelligence? Could it have led to fire, metallurgy, civilization? Then there's the Eocene epoch, about 56 to 33.9 million years ago. Following the extinction of the dinosaurs, mammals exploded into the ecological niches left behind. In that window, primates began to diversify. If intelligence had emerged among early mammals during this time and risen faster than we did, it could have had millions of years to flourish before being wiped out in another extinction event or lost to changing climates. And what about the oceans? Vast, deep, and poorly preserved in the rock record. Most marine sediments from tens or hundreds of millions of years ago are inaccessible, destroyed by subduction or deeply buried. If an intelligent aquatic species had risen in the deep sea, cephalopod-like beings, perhaps, building with materials that don't fossilize or leaving signs that erode easily, how would we ever know? There is something humbling in this realization: the fossil record is incomplete. The geological archive is imperfect. And even if we believe civilization must leave behind permanent scars, Earth is an efficient eraser. We typically assume that civilization is rare and recent. But if we allow for the full spectrum of time Earth offers, if we really embrace the idea of billions of years, we have to ask, why only now? Why only us? Is it truly the case that no intelligent civilization arose in all those silent ages? Or is it possible, just possible, that Earth's ancient story includes other chapters, ones long erased, written in languages we'll never decipher, in forms we'll never recognize, by species whose bones and tools were ground into oblivion? A billion years is not just a blank canvas, it is a vast, untouched gallery where any number of worlds might have been painted, only to be scraped clean by time itself. The idea that an advanced civilization could rise, flourish, and vanish entirely, leaving no visible trace, may sound implausible at first. After all, look around us: cities of concrete and steel, satellites in orbit, massive dams and power grids. Surely something would survive, right? But that belief, grounded in the familiarity of our present world, falters in the face of geological reality. Earth is not a static backdrop where history quietly accumulates. It is a dynamic, living planet, one that reshapes itself constantly. And over millions or hundreds of millions of years, even the most colossal human creations would be no match for the combined forces of erosion, tectonics, and crustal recycling. Let's begin with erosion, the slow but relentless sculptor of landscapes. Wind, rain, ice, and the movement of rivers gradually wear down even the hardest surfaces. The process is invisible over short timescales, but given enough time, erosion will reduce the tallest mountains to dust. Now imagine what it does to buildings. Stone is not immune. Metals rust, crumble, and dissolve. Concrete decays. Glass shatters and weathers. Even under the best conditions, unmaintained human structures begin to degrade in just decades. A modern city left to the elements could be reduced to rubble within a few centuries, and in 10,000 years, might be nearly unrecognizable. Scale that up to 10 million years. Then to 100 million. Vegetation takes over, roots breaking through asphalt and stone. Weather reduces structures to fragments. Animals and bacteria break down whatever remains. In cold, dry, or anaerobic environments, some artifacts might linger longer, but those are rare. And even then, exposure to oxygen, moisture, and temperature fluctuations accelerates decay. Now factor in tectonics. Earth's outer shell is divided into massive plates that drift slowly, just a few centimeters per year. But over millions of years, this movement is dramatic. Continents collide, giving rise to mountain ranges. Land masses rift apart, forming oceans. Entire regions are lifted, twisted, folded, and buried. A city built on a stable plain today could, in 100 million years, be uplifted into a mountain chain or subducted beneath another plate entirely. And once something is dragged into a subduction zone, sinking into the Earth's mantle, it's as good as gone. The rocks are melted. The records are erased. Then there's the phenomenon of crustal recycling. Unlike the Moon or Mars, which preserve ancient surface features for billions of years, Earth's surface is constantly recycled. Oceanic crust, for instance, is relatively young. Because it forms at mid-ocean ridges and is pushed outward by new crust, it eventually gets destroyed at subduction zones. The oldest seafloor we've found is only around 200 million years old. That means any coastal or marine civilizations from earlier than that would now be lying beneath miles of new crust, or no longer exist at all. Even on land, rocks are constantly weathered, buried, and metamorphosed. Layers of sediment compress into stone, then get pushed deeper, transformed by heat and pressure into entirely new rock types. In this process, most traces of past surface life are obliterated, fossils crushed, structures pulverized, artifacts turned into mineral grains. Think about what remains from the Roman Empire, a civilization just 2,000 years old. Some temples. A few aqueducts. Foundations. Much of it already lost to time. Now imagine what would remain of us after 100 million years, after being buried, melted, crushed, and eroded beyond recognition. Perhaps a few fragments of ceramics. A chemical signature in the rocks. A thin layer of unusual isotopes. That's it. Even our technological byproducts, plastics, radioisotopes, synthetic compounds, may degrade or be indistinguishable from natural materials after millions of years. And if a prior civilization had a different technological basis, one that didn't rely on combustion, fossil fuels, or plastics, its remains might not be detectable even in theory. So yes, a civilization could leave no trace. It could build and explore, discover and create, love and die, and then be swallowed by the earth. And the deeper we look into the planet's past, the more we realize how few pages of that ancient book we still hold. The question then becomes, how many pages have already been lost? Fossilization is extraordinarily rare, not just in terms of what we find, but in terms of what can be preserved at all. It's easy to look at a museum full of dinosaur skeletons and imagine that the past is thoroughly documented. But in truth, the fossil record is a fragmented, biased sample of life's ancient history. The overwhelming majority of organisms that have ever lived, by some estimates, over 99.9%, left no trace behind. They decomposed, were eaten, scattered by wind or waves, or dissolved back into nature's endless cycles. They vanished without a fossil, without a footprint, without a whisper. This rarity is due to the very specific and unforgiving conditions required for fossilization. First, the organism must escape the usual fate of decay. That often means rapid burial, by mud, volcanic ash, sand, or silt, so that oxygen, bacteria, and scavengers can't destroy it. Then it must survive the immense pressures, chemical reactions, and tectonic shifts that come with burial over geological timescales. Even then, only certain materials fossilize well. Hard parts, bones, shells, teeth, are more likely to endure. Soft tissues, skin, and organs? Almost never. And even among bones, many dissolve or break apart long before mineralization can occur. Now imagine how this reality applies not to biological life, but to the byproducts of civilization, specifically, to technology. Technology, for all its resilience in daily life, fares even worse in deep time than bones. Most of our tools, devices, and structures are made of materials that are far less likely to fossilize than calcium-rich skeletons. Metals corrode. Plastics degrade. Electronics fragment into dust. Wood rots. Glass weathers. Concrete breaks down. Even silicon, which forms the basis of modern computing, is ultimately vulnerable to the slow grinding forces of geological activity. Artifacts of our world might last hundreds, maybe thousands of years if left undisturbed. But deep time demands survival on the order of millions of years. And that's a different game entirely. Even our most durable materials are no match for what Earth throws at them. Consider plastics. Modern plastics didn't exist before the 20th century. And we know they can last hundreds or even thousands of years in the environment. But in geologic terms, even that is fleeting. Exposure to ultraviolet light, oxygen, heat, and microbial activity accelerates degradation. Eventually, plastics break down into microscopic particles, and even those might not remain distinct in the sedimentary record. Metals, another key part of civilization, corrode relentlessly. Iron rusts. Aluminum oxidizes. Copper patinas, then degrades. Without active protection or sealed storage, metal tools and structures will vanish. And in natural environments, especially those rich in water, acids, or salts, corrosion is inevitable and swift. Given enough time, a skyscraper becomes iron dust. A circuit board becomes meaningless debris. Even if some remnants do survive long-term, their recognizability is another challenge entirely. Suppose a fragment of synthetic polymer, or a shard of fused metal glass, somehow endured millions of years encased in rock. What would it look like to a future geologist? Would it even be recognized as artificial? Or would it be dismissed as a strange mineral inclusion, a geologic curiosity rather than a technosignature? The very idea of technology-based fossilization is a contradiction in terms. Fossils form when nature preserves nature. But technology is the result of intelligent manipulation. It's artificial, ephemeral, often chemically unstable. Civilization doesn't fossilize the way trilobites or ammonites do. It decays, scatters, and eventually blends into the environment so thoroughly that its edges vanish. And that leads to a haunting question. If our civilization were to collapse today, what would remain in 10 million years? In 100 million? Would anything survive long enough to be recognized as the work of intelligence? Or would we dissolve entirely into the layers of stone and silence, just like any other vanished species? If a past civilization existed before us, built cities, crafted tools, discovered science, altered its world, then unless it left behind truly indestructible artifacts in truly undisturbed places, it may have disappeared so completely that even our best science would miss it. In that context, the absence of evidence is not necessarily the evidence of absence. It may just be the result of time's incredible ability to forget. If civilizations can vanish almost entirely over millions of years, dissolved by erosion, buried by tectonics, or corroded by time, then how would we ever know one existed? What kind of evidence could possibly survive Earth's geologic churn? The answer may lie not in visible artifacts like buildings or machines, but in what scientists call technosignatures, subtle but measurable fingerprints of technology that linger in the environment, long after the civilizations that created them are gone. Technosignatures are not about finding ancient ruins. They are about recognizing unnatural patterns, chemical, isotopic, or structural anomalies in the Earth's layers that don't quite belong. Unlike a fossil or an arrowhead, technosignatures could outlast the civilization itself by orders of magnitude. They are less about direct observation and more about deduction. If something altered the natural world in a way nature can't easily explain, it might have been intelligent. So what technosignatures might an industrial civilization, whether human or something long forgotten, actually leave behind? Let's begin with plastics. These synthetic polymers didn't exist naturally on Earth before the 20th century, and now they are everywhere, from the deepest trenches of the ocean to the peaks of remote mountains. Plastics resist decomposition better than most organic substances. In the short term, they persist in landfills, oceans, and soils. In the long term, they begin to fragment, first into microplastics, and eventually into nanoplastics, small enough to enter the geological record. Some researchers speculate that future geologists might find a distinctive, plastiglomerate layer, rocks fused with plastic debris, in Earth's sedimentary strata. This would be a clear technosignature, a material that nature doesn't produce on its own. But the real question is whether these synthetic molecules can endure not just hundreds or thousands, but millions of years. Some might, especially those buried in oxygen-free environments or fused with minerals. Others may chemically degrade and disappear entirely. If a previous civilization used plastics, there's a slim chance traces could still exist, if we know where and how to look. Next are isotopic anomalies, subtle fingerprints left by industry, agriculture, and energy production. One powerful example is the change in carbon isotopes caused by burning fossil fuels. Modern human activity has dramatically increased atmospheric CO2 levels, and this has a measurable isotopic signature, specifically, a decrease in carbon-13 relative to carbon-12. This ratio is shifting in a way that future geochemists could potentially detect millions of years from now, preserved in ice cores, carbonate layers, or marine sediments. Similarly, industrial-scale nitrogen use, particularly synthetic fertilizers, has changed the isotopic signature of nitrogen in the soil and oceans. These changes, if buried under layers of new sediment, could form a chemical line in the geological record, one that future civilizations, or present-day scientists, might interpret as the result of technological activity. Then there's the issue of metals and rare elements. Industrial civilization uses large quantities of elements like lead, mercury, chromium, and cadmium, materials that do occur in nature, but not in the concentrated and widespread patterns that result from human activity. If a past civilization also mined and refined metals, traces might remain in unexpected sediment layers, or as pockets of slag, industrial waste material. More telling would be the presence of highly processed alloys or non-naturally occurring isotopes, which cannot form without technological intervention. One of the most intriguing possibilities lies in radioactive isotopes, materials that either don't exist in nature or exist only in trace amounts, but are produced in large quantities by nuclear reactors or weapons. Elements like plutonium-244 or certain isotopes of cesium and strontium could act as nuclear technosignatures. These isotopes decay over time, but some have half-lives long enough that they might still be detectable millions of years later, embedded in sedimentary layers. If a past civilization harnessed nuclear energy, or suffered a nuclear catastrophe, some radioactive trace might remain, waiting to be found. Beyond the chemical and isotopic, there's the possibility of unusual mineral formations. Certain industrial processes produce synthetic minerals or modify existing ones in ways that don't occur naturally. For example, high-temperature ceramics, glass-like materials from explosions, or metallic microspheres from combustion. If these were somehow buried quickly and preserved in sedimentary rock, they might be detectable by their structure, composition, or formation environment. And let's not forget global warming itself. The current spike in temperature, sea level, and atmospheric carbon might seem like a purely biological or environmental event, but it could also become a lasting technosignature. If similar patterns appear in ancient records, sudden CO2 rises, unusual temperature spikes, mass extinctions, they could, in theory, be linked to a past civilization's industry. This is, in fact, one of the key ideas behind the Silurian hypothesis, that the Earth's past might contain environmental fingerprints similar to our own, and that these might point to more than just natural causes. Yet the greatest challenge remains interpretation. A technosignature, by definition, is only meaningful if we recognize it as such. A spike in metal concentration, an odd isotopic anomaly, a strange mineral deposit, these might all be dismissed as natural, unless there's context. Without a Rosetta Stone or a visible artifact, science is cautious to jump to conclusions. And rightly so. But that caution also means that if there was a civilization in the deep past, we might have already seen its fingerprints, and quietly filed them away under geologic anomaly. Ultimately, the search for technosignatures from ancient Earth is a new frontier, one where geology meets archaeology, and where science fiction edges into scientific method. The absence of skyscrapers or pyramids in 100-million-year-old rocks doesn't mean the story is empty. It just means the traces, if they exist, are subtler than we expected. And maybe, just maybe, they're still waiting to be noticed. If a civilization had once risen and fallen deep in Earth's past, tens or even hundreds of millions of years ago, what physical signs could possibly remain? Not their buildings, not their machines, not their books or languages, but something much more elusive, changes to the planet itself. Alterations to the global environment. Chemical fingerprints. Shifts in temperature, carbon levels, and metal concentrations that have no easy explanation. In short, geological evidence of industry. This is the realm of clues left not by intention, but by consequence. Industrial civilizations, at least as we understand them, transform their planet. They burn fuel, alter atmospheres, mine resources, change ecosystems. And in doing so, they may leave behind broad, planetary-scale signals. Let's begin with carbon spikes. The burning of fossil fuels releases enormous amounts of carbon dioxide into the atmosphere, particularly carbon that is isotopically light, meaning it contains a lower ratio of carbon-13 to carbon-12. This shift is detectable in sediment, and ice cores as a drop in the Delta-13C value, and it's already happening now, thanks to human activity. If this continues, future geologists might see our era as a sharp, unnatural carbon event in the stratigraphic record. But that raises an intriguing question. Have we seen this kind of carbon anomaly before? The most famous example is the Paleocene-Eocene thermal maximum, PTM, which occurred around 56 million years ago. During this period, the Earth experienced a sudden and dramatic rise in global temperatures, up to 8 degrees Celsius in some regions, accompanied by a massive carbon isotope excursion. The source of that carbon remains a mystery. Some theories suggest volcanic activity, or the release of methane hydrates from ocean sediments. But the carbon came fast and was sustained. From a geological perspective, it looks eerily similar to what we're seeing now, an abrupt spike in greenhouse gases, ocean acidification, species migration, and mass extinction. Could the PTM have been caused by a past industrial civilization? That's the kind of question the Silurian hypothesis dares to ask, not to claim an answer, but to reframe the unknown. In addition to carbon shifts, temperature anomalies offer another line of evidence. Global warming and cooling events leave traces in the rock and ice. Fossils from different latitudes migrate up or down in the strata. Sea levels rise or fall, altering sedimentation patterns. Ice cores record the ratios of oxygen isotopes that correspond to changing temperatures. These are planetary scale events, and while many have natural explanations, orbital changes, volcanic activity, asteroid impacts, not all are fully understood. If a prior civilization used carbon-based fuels or altered the landscape on a global scale, it might have triggered warming or cooling that looks similar to natural events. But if the magnitude or timing of those changes doesn't fit the expected causes, it opens the door to other possibilities, including the technological. Then there's the case of metals and industrial byproducts. Civilizations mine and process rare elements. They refine copper, iron, aluminum, and alloys. these don't just vanish. Mining activity can distribute heavy metals into soil, rivers, and oceans. Modern human industry has created noticeable spikes in lead, mercury, arsenic, and cadmium concentrations in sediments, especially near major urban centers or along coastlines. In deep time, these elements can persist, especially if they're trapped in anaerobic, oxygen-free layers where decay is minimized. So if there were a prior civilization, we might expect to find unusual concentrations of industrial metals in specific geological layers, particularly if the civilization had entered a phase similar to our own industrial revolution. Even more telling might be the presence of synthetic materials or non-naturally occurring compounds. For example, persistent organic pollutants (POPs), chlorofluorocarbons (CFCs), or other long-lived industrial chemicals can embed themselves in sediments or ice. Though they degrade over time, traces might remain in closed, undisturbed environments. Some materials used in electronics and modern technologies, like certain rare earth elements, are not typically concentrated in natural settings. Their unexpected presence in ancient sediments could be a red flag. There's also evidence from ash layers and stratigraphic disruptions. Civilization reshapes the land. It clears forests, alters coastlines, builds dams and roads. These changes can affect erosion patterns and sedimentation. Human civilization, for instance, has created a sharp increase in sediment flowing into the oceans due to deforestation and agriculture. This would be visible as a sudden thickening of particular sediment layers, potentially mimicking natural floods or tectonic uplift, but with different geochemical signatures. And then there's the matter of extinctions. Industrial civilization exerts enormous pressure on ecosystems. Habitat loss, pollution, climate change, and overhunting contribute to rapid biodiversity loss. Right now, many scientists believe Earth is undergoing a sixth mass extinction, one driven not by asteroids or supervolcanoes, but by human activity. If a previous civilization existed, similar ecological impacts might have occurred. A sudden and unexplained drop in biodiversity, coupled with anomalous chemical or isotopic data, might hint at a civilization-induced crisis. The challenge lies in distinguishing between natural and unnatural causes. Volcanic eruptions, asteroid impacts, and methane releases can all trigger carbon spikes and extinctions. But a civilization would leave different fingerprints, subtle, perhaps, but identifiable with the right context. Multiple simultaneous anomalies, carbon, metals, synthetic compounds, sudden extinctions, could form a pattern too specific to ignore. So, what have we seen? We've found unexplained carbon isotope excursions, sudden temperature shifts, isolated layers rich in metals or ash. Events like the PTM, the Triassic-Jurassic extinction, and the mid-Miocene climatic optimum stand out as curious moments in Earth's history. None are currently attributed to intelligence, but they show us how civilization-scale impact can look from deep time's perspective. And perhaps, one day, someone digging through Earth's layers will stumble upon a stratum not quite natural. A line that doesn't belong. A scar in the stone, too precise, too sudden, too strange. A whisper from a world that came and went long before our own. The Paleocene-Eocene thermal maximum, commonly abbreviated as PTM, is one of the most mysterious and striking events in Earth's geologic history. Occurring approximately 56 million years ago, it marks a period of intense global warming that lasted for around 100,000 to 200,000 years. In the context of the Silurian Hypothesis, the PTM is a focal point, not because we have definitive proof of an ancient civilization tied to it, but because it so closely mimics the environmental and atmospheric changes we see today, those caused by industrial civilization. The PTM begins suddenly, at least geologically speaking, with a dramatic and rapid rise in global temperatures. In a span of just a few thousand years, a blink on the geological timescale, average global temperatures shot up by 5 to 8 degrees Celsius. The Arctic was warm enough to host palm trees. The oceans turned acidic. Sea levels rose. There were mass migrations of animal species, extinctions of deep-sea life, and major shifts in ecosystems. All of these symptoms echo what modern scientists warn might be ahead if anthropogenic climate change continues unabated. But here's what makes the PTM especially strange: the carbon isotope excursion. This term refers to a sudden drop in the ratio of carbon-13 to carbon-12 in the atmosphere and oceans, which is exactly what we observe today due to the burning of fossil fuels. Fossil fuels are composed of ancient organic matter, rich in carbon-12, the lighter isotope. When burned, they release a distinctive isotopic signature into the environment. The PTM shows the same isotopic shift, suggesting that a massive infusion of light carbon entered Earth's systems all at once. But where did it come from? That's the mystery. Several hypotheses have been proposed, none of which fully explain the scale and speed of the event. One idea is that there was an enormous volcanic eruption in what is now the North Atlantic, triggering the release of carbon dioxide and methane. Another proposes that massive methane hydrates, trapped in ocean sediments, suddenly destabilized and released their greenhouse gases into the atmosphere. Yet another theory speculates that peat or coal deposits might have combusted in enormous fires due to tectonic shifts. Still, these natural explanations, while plausible in pieces, leave gaps. None of them fully account for the precision of the carbon isotope anomaly, or the rate at which climate change occurred. This is where the Silurian hypothesis enters, not with certainty, but with curiosity. If we were to examine the PTM without assuming it had to be natural, we might see its signature as suspiciously similar to what we ourselves are doing today. Could an earlier civilization have existed before the PTM and triggered it, knowingly or unknowingly? It's a provocative question, and one that the scientific community approaches cautiously. Gavin, Schmidt, and Adam Frank, who first formalized the Silurian hypothesis, don't claim a past civilization did cause the PTM, but they ask us to consider how such an event would look from tens of millions of years in the future. If our industrial age were to end tomorrow, and a new intelligent species evolved 56 million years later, would they be able to recognize us? Or would our carbon spike, our extinction footprint, and our isotope trails appear to them the way the PTM appears to us? It's important to note that the PTM is not the only carbon anomaly in Earth's past, but it is the most closely studied, and the most analogous to what we might call a civilization-level impact on the planet. For that reason, it has become the central case study for imagining what kind of technosignature or geological fingerprint a prior civilization could leave behind. Other phenomena during the PTM further amplify the intrigue. Sedimentary records show a global reduction in oxygen levels in the oceans, possibly due to a surge in organic matter dying off, decaying, and consuming available oxygen. That oxygen loss would have led to dead zones and mass extinctions in the deep sea, much like the ones we're currently seeing spread due to runoff and warming oceans. There's also evidence of extreme weathering, rocks and soil breaking down rapidly due to increased rainfall and heat, suggesting an intensification of the hydrological cycle. Again, a parallel to today's trends. The PTM also coincides with a sharp rise in insect diversity and plant damage, possibly due to a runaway feedback loop. More heat means more plant growth, more herbivory, more CO2, and more warming. Sound familiar? And yet, for all this chaos, the Earth eventually stabilized. The warm period ended. The carbon dissipated or was buried. The climate cooled. Life adapted. But the question lingers, was the PTM a natural geological event with eerily modern echoes? Or a civilization-level planetary disruption, erased by time? From the perspective of a species millions of years removed, how would we distinguish between a natural warming and a technological one? The parallels are haunting. They don't prove anything conclusively, but they show that if an industrial civilization had existed before us, and if it had ended in a global environmental crisis, we might expect to find something that looks exactly like the PTM. Perhaps we already have. Mass extinctions are Earth's brutal reset button, vast, sweeping events that erase dominant species, disrupt ecosystems, and leave behind a world forever changed. They are both destroyers and originators, tearing down the familiar to make room for the new. Throughout Earth's history, at least 5 major mass extinctions have drastically altered the course of evolution, and many smaller ones have nudged the planet's biosphere in different directions. But beyond their biological significance, these events raise a compelling question: could they have also ended civilizations we never knew existed? To explore that, we need to understand how sudden and catastrophic these events can be, and how little time a civilization might have to prepare. Perhaps the most famous example is the Cretaceous, Paleogene extinction event, which occurred around 66 million years ago. A 10-kilometer-wide asteroid slammed into the Yucatan Peninsula, carving out the Chicxulub crater and unleashing a planet-wide apocalypse. The impact vaporized rock and water, ejecting vast quantities of debris into the atmosphere. Firestorms ignited across continents. A global blackout followed, as sunlight was blocked by dust and aerosols. Temperatures plummeted. Photosynthesis ceased. Food chains collapsed. In a geological instant, roughly 75% of all species were wiped out, including the non-avian dinosaurs. If an intelligent, technological species had existed at that time, perhaps occupying coastal regions or tropical zones, it could have been utterly erased. Their cities crushed by tsunamis. Their skies choked with fire. Their infrastructure buried beneath layers of ejecta and sediment. Within a few millennia, all traces of their world could be hidden beneath new strata, overwritten by the rebirth of ecosystems that followed. But asteroids aren't the only culprits. Supervolcanoes are another terrifying force of mass extinction. These are volcanic eruptions on a scale far beyond anything humans have witnessed, events that can spew thousands of cubic kilometers of ash, gas, and lava into the atmosphere and across continents. The Siberian traps and Deccan traps are ancient examples, both implicated in mass extinction events. The Siberian traps, for instance, are thought to have contributed to the Permian-Triassic extinction, the most devastating extinction event in Earth's history, around 252 million years ago, when over 90% of marine species and 70% of terrestrial species vanished. Supervolcanic eruptions release not just lava but also massive amounts of sulfur dioxide, which can cool the planet, and carbon dioxide, which can later trigger warming. The result is a climate roller coaster, global cooling followed by hothouse conditions. Oceans can acidify, food chains disintegrate, and ecosystems collapse. If a civilization relied heavily on agriculture, global infrastructure, or complex trade networks, a supervolcano's effects could be catastrophic. Ash clouds could blanket entire continents, shutting down sunlight and weather systems. Crops would fail. Societies would face starvation, disease, and chaos. And if such an event were to occur during a period of environmental fragility, it could be the final blow. There's also climate instability, driven either by natural cycles or civilization-induced activity. Rapid shifts in temperature, sea level, or atmospheric composition can be just as devastating as an asteroid or eruption, especially if they unfold over just a few generations. Take, for example, the Younger Dryas, a sudden cold snap that occurred around 12,800 years ago. It reversed the warming trend of the last ice age and plunged much of the northern hemisphere back into glacial conditions. The cause is still debated. Possible triggers include a burst glacial lake, changes in ocean currents, or even a comet impact, but the effect was dramatic. Ecosystems changed, megafauna went extinct, and early human cultures may have been severely disrupted. Now imagine a more advanced civilization facing a similar or even sharper climate swing. Glaciers advance. Croplands freeze or dry out. Coastal cities vanish beneath rising seas. If the shift is fast and global enough, even a technologically advanced society might not be able to adapt in time. Civilizations depend on stability. They require predictable seasons, accessible resources, and interconnected systems. When these systems break down, whether through impact, eruption, or abrupt climate change, the shock can be terminal. What begins as an environmental crisis can cascade into societal collapse. Infrastructure decays. Knowledge is lost. And in time, the ruins are buried beneath sediment, forests, or seas. But mass extinctions do more than destroy. They open up ecological space. After each reset, evolution surges forward, filling the voids with new forms of life. The age of mammals followed the fall of the dinosaurs. Could the rise of our species have followed the fall of a previous intelligent one? We don't know. But the timing is possible. The sheer number of extinction events in Earth's history leaves multiple windows during which intelligent life could have emerged, risen to dominance, and vanished, without ever meeting us. And the farther back in time we look, the blurrier the picture becomes. Even if only one advanced civilization arose before us, even if it lasted just a few thousand years, and ended in fire, ice, or silence, it might have been buried so thoroughly by the Earth's violence that we will never find it. Unless we know exactly what to look for. The Cambrian explosion is one of the most dramatic and enigmatic chapters in the history of life on Earth. Occurring roughly 541 million years ago, it marks a relatively brief period, geologically speaking, in which an astonishing diversity of complex, multicellular life suddenly appears in the fossil record. Trilobites, early arthropods, sponges, mollusks, and other bizarre forms of life emerged in a flourishing, almost abrupt evolutionary burst. But what if this moment of diversification wasn't the true beginning of complex life? What if something intelligent had existed before this explosion, something that came, evolved, and vanished so completely that even the fossil record does not remember it? To ask that question is to peer into the most obscure and poorly understood period in Earth's biological history, the Precambrian, a stretch of time that spans nearly 4 billion years before the Cambrian began. In those long eons, life existed. We know this from stromatolites, layered structures formed by microbial mats, that date back over 3.5 billion years. We know it from microfossils and isotopic evidence that suggests biological activity was shaping Earth's chemistry long before animals had even evolved. But that life was largely microbial, simple, single-celled organisms floating in ancient seas. For billions of years, complexity seemed to stall. Then, almost inexplicably, the Cambrian explosion happened, and with it, the blueprint of modern life was born. So, could intelligence have evolved during that unimaginably long stretch of time before the Cambrian? Could there have been a rise and fall that left no clear mark? It might sound implausible at first. How could intelligent life exist without leaving behind fossils or tools? But when we consider how little we know about the Precambrian biosphere, the idea becomes less far-fetched. The vast majority of rocks from that time have been metamorphosed, subducted, or eroded. The crust has been recycled, crushed, or melted. Whatever fragile fossils once existed have likely been obliterated. And if an intelligent species had developed tools or technology during that time, we would face the same challenges discussed earlier. Those materials might not fossilize, and even if they did, they might be buried under billions of years of geological activity. Furthermore, we must challenge a key assumption, that intelligence can only arise from animals that look or behave like us. Our view of intelligence is shaped by our evolutionary path: vertebrates, large brains, hands, tools. But intelligence might arise from a completely different trajectory. It could be based on entirely different biological structures, maybe neural nets in soft-bodied creatures, or information processing in colonial organisms, or even biochemical communication across networks of microbial mats. If intelligence did evolve during the Precambrian, it may have looked nothing like human cognition or anatomy. And if it left behind traces at all, they would likely be invisible to our current scientific lenses. One theoretical possibility is that intelligence emerged in a soft-bodied lineage, organisms without hard shells, bones, or teeth. Such creatures rarely fossilize. Even today, soft-bodied animals like jellyfish and worms are severely underrepresented in the fossil record. The famous Burgess Shale fossils from the Cambrian, a rare window into soft-bodied life, only exist because of an extraordinary set of preservation conditions. If a similar intelligent species evolved in the Precambrian, and their world did not undergo such exceptional preservation, then we may have no trace of their existence at all. Another possibility is that intelligence didn't evolve on land, but in deep oceans, in subsurface biospheres, or beneath polar ice. environments like these are poorly preserved in the rock record. They are remote, constantly shifting, and geochemically volatile. If intelligent beings developed in such niches, especially early in Earth's history, their remains could be inaccessible, obliterated, or misinterpreted. And there's the question of timescale. The Cambrian explosion happened in a burst, lasting 20 to 25 million years, an eye blink geologically, but a vast span for a civilization. If intelligence had evolved during the Ediacaran period, for example, just 20 or 30 million years before the Cambrian, we might see no trace of it today, even though it could have thrived for longer than modern humans have existed. A civilization that flourished for 10,000 years, or even 100,000 years, could be wiped clean by a single extinction event, followed by eons of tectonics and erosion. Time erases more than it preserves. It's also worth noting that the transition into the Cambrian is not a sudden on-off switch. There were precursors to the Cambrian fauna, organisms from the Ediacaran period with strange, soft bodies and no clear descendants today. Some of these organisms, like Dickinsonia or Sprigina, remain evolutionary mysteries. They appear alien, unlike any modern animals. What if some of them were early experimentations in complexity, lineages that explored cognition, cooperation, or even rudimentary intelligence before vanishing in the ecological upheaval that ushered in the Cambrian explosion? Even more speculative is the idea that the Cambrian itself was a reset, that some global catastrophe cleared the biosphere, paving the way for a new evolutionary wave. If an intelligent species arose before the Cambrian, and it altered its environment, through overuse, climate manipulation, or war, the resulting collapse might have left the planet chemically altered. Some scientists even wonder whether a sudden oxygenation event that preceded the Cambrian might have involved unusual biological or chemical feedbacks. While these are not accepted as technosignatures, they show how planetary scale changes can happen suddenly, and leave ambiguous evidence. The Cambrian explosion is a pivot point, a before and after in the fossil record. But its sharp boundary may not reflect a true beginning. It may simply be the moment when conditions became ideal for fossilization. What lies before it is largely obscured, hidden in ancient stone and time-worn fragments. If we one day discover evidence of intelligence in that abyss of deep time, subtle anomalies, unexplained patterns, or unaccountable shifts in Earth's chemistry, it could rewrite the story of evolution. It could reveal that we are not the first, not the original creators of tools, knowledge, or culture. Just the latest echoes in a much older chorus. The deeper we go into Earth's geological record, the more ancient and alien the world becomes, but also, paradoxically, the quieter. Not in terms of time or activity, but in terms of what survives. This quiet is what scientists sometimes refer to as the silence in the sediment, a profound absence of information in the very places we look to understand Earth's deep past. It is a silence that hides not only forgotten ecosystems or extinct species, but potentially entire chapters of planetary history, chapters that may have once included civilizations, perhaps even intelligent ones, erased by the slow and relentless passage of time. Sediment, after all, is Earth's journal. It's where rainstorms, volcanic eruptions, floods, animal migrations, and even mass extinctions leave their mark. With enough patience, scientists can extract meaning from these layers like sentences in stone. Fossils might tell us who lived. Isotopes might tell us what the climate was like. Ash layers might pinpoint catastrophe. But this journal is flawed. It is heavily edited, with entire pages torn out, rewritten, or never recorded at all. And when it comes to signs of civilization, especially ancient or technological ones, this silence becomes deafening. Why? Because most of the processes that preserve Earth's history are incredibly selective. First, only a small fraction of Earth's surface is ever buried under sediment in the right way to preserve a record. Erosion, tectonics, and biological activity destroy or recycle surface layers constantly. The ocean floor, for example, is mostly young, none of it older than 200 million years. Because tectonic plates constantly push new crust outward and subduct old crust into the mantle. That means any evidence of a civilization that once lived on the ocean floor, like a hypothetical underwater society, would have long since been dragged into the earth and melted. Even on land, preservation is tricky. Forests, mountains, and plains are dynamic. They erode, shift, flood, and burn. If a civilization built its cities in such regions, and most likely would, due to water and resources, then those sites would be the first to vanish over geological time. Only in rare cases do cities or structures get rapidly buried under volcanic ash, mudslides, or sedimentation from floods. Without such quick burial, wind, rain, and plant life eventually return everything to dust. Second, even when material is buried, fossilization is rare. Most organic material decomposes. Most artifacts decay. Metals corrode. Plastics degrade. Electronics break down. What remains might be a few stable isotopes, microscopic fragments, or disrupted mineral patterns, and that's if we're lucky. But there is no guarantee that these signs would survive long enough, or that they'd be preserved in places where we're currently looking. Then comes the third and perhaps most frustrating reason for the silence: access. Even when sedimentary layers from deep time are intact and potentially informative, they're often buried under miles of rock, inaccessible to drills or exploration. The best places to study ancient sediments are often remote, dangerous, or restricted. And most of the Earth's crust remains unexplored, a mystery hidden beneath our feet. Even when we do find ancient sediments, interpretation is a challenge. A strange isotopic anomaly might be attributed to volcanic activity. An unusual mineral layer could be explained as the result of a meteorite impact. Without a clear artifact, a tool, a structure, an unmistakable engineered material, mainstream science will lean toward the natural explanation. This is the scientific method at work, cautious and conservative by design. But it also means that the signal of a long-lost civilization could be hiding in plain sight, dismissed as geological oddity. Moreover, the sedimentary record is uneven. Some periods of Earth's history are richly recorded, like the late Jurassic or the Cretaceous, while others are sparse or blank. These unconformities in the rock record represent time lost, eras for which no rock layers exist, either because they were never deposited or were later eroded. It's entirely possible that key events, turning points, or entire civilizations existed during these gaps. This patchwork of preservation creates a narrative filled with blind spots. For instance, the Ordovician Silurian extinction event is recorded in some places, but not in others. The sudden appearance of complex animals in the Cambrian might represent a biological explosion, or just the beginning of better fossil preservation. We don't know what we don't know. Even the discovery of fossilized human ancestors is rare and regionally concentrated. Most of our evolutionary history is inferred from a handful of bone fragments. If we, a civilization less than 300,000 years old, left such a limited and contested footprint, what would be left of a civilization from 300 million years ago? And herein lies the mystery. The sediment is both a record and a veil. It speaks, but in whispers. It holds truths, but only fragments. It answers questions we haven't yet asked and hides stories we may never uncover. The silence in the sediment isn't a failure of science, it's a challenge, an invitation to look harder, deeper, and with more imagination. Because somewhere, beneath our feet, behind the noise of erosion and entropy, could lie the faintest echo of a forgotten intelligence. One that rose before us. One that fell. And one that left behind no more than a question etched into ancient stone. Imagine a time when the continent we now call Antarctica was not a frozen wasteland, but a thriving, temperate land, covered in forests, rivers, and possibly even teeming with life. This isn't science fiction. Geological and paleobotanical evidence confirms that during multiple warm periods in Earth's distant past, Antarctica was far from the icy desert we know today. And that simple fact cracks open a door to an idea both extraordinary and unnerving. Could an intelligent civilization have once developed on Antarctica, hidden now beneath miles of ice? To understand the plausibility, we first need to step back and look at Antarctica's ancient climate history. Roughly 34 million years ago, during the late Eocene epoch, the Earth entered a major cooling phase. Before that, Antarctica was covered in dense vegetation, including temperate rainforests. Fossilized tree stumps, pollen, and leaf impressions all confirm that the continent once hosted lush ecosystems. Even more startling, during the mid-Cretaceous period, around 100 million years ago, Antarctica may have been a subtropical paradise, with average temperatures in the range of 15 to 20 degrees Celsius, 59 to 68 degrees Fahrenheit. During these warm periods, Antarctica wasn't buried under a thick sheet of ice. Instead, it had river systems, coastlines, lakes, and a land bridge connecting it to Australia. These conditions lasted for tens of millions of years, plenty of time, from an evolutionary standpoint, for complex life to develop. And where complex life thrives, there exists the possibility, however remote, that intelligence could arise. But if a civilization did evolve in prehistoric Antarctica, why haven't we found it? The answer may lie in the continent's transformation. Around 34 million years ago, as global temperatures declined and Antarctica drifted farther south, the Antarctic Circumpolar Current formed. This powerful oceanic current isolated the continent from warmer waters and triggered the accumulation of permanent ice. Over time, glaciers and ice sheets grew, eventually entombing the entire landmass beneath kilometers of ice. Today, the Antarctic ice sheet holds about 90% of the world's freshwater and conceals a land surface we can barely observe directly. This glacial cover poses a profound challenge to archaeology. Any remnants of a hypothetical Antarctic civilization, cities, tools, artifacts, would now be deeply buried and largely inaccessible. Satellite imaging and ground-penetrating radar can reveal subglacial mountains, valleys, and lakes, but not the fine details that would suggest cultural activity. The weight of the ice itself, millions of tons pressing down, would have crushed and deformed most man-made structures. And any organic materials left behind would likely be long decayed, unless preserved in some extremely unusual microenvironment. That said, Antarctica does contain some intriguing features. One is Lake Vostok, a massive freshwater lake sealed beneath nearly 4 kilometers of ice. Isolated for perhaps 15 million years, it is one of the largest subglacial lakes in the world. Scientists have speculated that such environments could support microbial life or even complex ecosystems, cut off from the surface world, operating on their own terms. If life can persist there now, might more complex life have once thrived above or around it before the ice came? There's also the Gambrintsev mountain range, a mysterious chain of mountains the size of the European Alps, completely hidden beneath the central East Antarctic ice sheet. These peaks rise thousands of meters but are utterly buried in ice. Their topography, revealed only through remote sensing, has never been directly explored. Could these mountains have once supported an ancient civilization? If so, their ruins would now lie in darkness and extreme pressure, unreachable by current methods. Skeptics will rightly point out that we have no hard evidence of any civilization in Antarctica before the ice came. No tools, no buildings, no bones, nothing. But then again, how could we? If you were to design a place on Earth where the passage of time would completely erase any trace of intelligent life, Antarctica is about as close to perfect as it gets. Its isolation, inaccessibility, and glacial overburden ensure that even advanced civilizations would vanish without a whisper. There's also a deeper philosophical question at play here. How would we even recognize the remnants of a civilization from tens of millions of years ago, especially if it took a different evolutionary or technological path? What if their buildings were made from organic or biodegradable materials? What if their communication or storage systems left no durable physical record? Our current understanding of civilization is rooted in our own industrial model, steel, concrete, data servers, but intelligence might not always leave such footprints. The idea of a subglacial civilization beneath Antarctica has captured imaginations in fiction and conspiracy theory alike, from Lovecraft's At the Mountains of Madness to fringe claims of hidden alien bases. But even when stripped of such embellishments, the core scientific question remains valid: what lies beneath Antarctica's ice? Could a species have flourished there during one of Earth's warm greenhouse periods, only to be erased by the slow freeze of time? Could tectonic uplift or volcanic activity one day reveal fossilized traces of culture, structure, or even tools? Could drilling efforts, such as those ongoing in subglacial lakes, eventually stumble upon something unexpected, something ancient and non-random? At present, we simply don't know. The technology to explore Antarctica's full geological and archaeological past is in its infancy. The cost and difficulty are immense. But the scientific intrigue grows. Because in the silence beneath the ice, the possibility remains that we are not the first to ponder existence, to build, to wonder, to fall. The ocean floor is one of the most mysterious and least explored environments on Earth. It stretches over 70% of the planet's surface and hides some of the deepest, darkest, and oldest terrains known to science. And yet, despite its vastness, we have mapped less of the deep ocean than we have the surface of the Moon or Mars. With that in mind, a haunting possibility emerges. Could an intelligent civilization have once thrived beneath the sea, hidden in the abyssal plains, continental shelves, or ancient undersea plateaus, and now lie buried forever under layers of sediment, unreachable and undetected? To understand the plausibility, we must first reimagine what civilization means. Modern humans have built their empires on land, where agriculture, metallurgy, and large-scale architecture can flourish. But intelligent life doesn't necessarily need to follow our path. If a species had evolved in the ocean, perhaps descended from cephalopods, aquatic reptiles, or entirely unknown organisms, it would have faced different challenges and opportunities. And if they developed technology suited to their environment, it may have looked nothing like what we associate with civilization, no skyscrapers or steel bridges, but perhaps bioengineered coral structures, light-based communication, or materials adapted to withstand high pressure and saline chemistry. The deep ocean offers an environment rich in geothermal energy, mineral resources, and ecological niches. Hydrothermal vents, for example, support entire ecosystems without sunlight, driven purely by chemical energy. These black smokers teem with life, tube worms, bacteria, crustaceans, often thriving in temperatures and pressures once thought uninhabitable. If nature can produce such complexity in extreme conditions, could intelligence not have arisen there as well? And even if an oceanic civilization didn't originate there, what if a land-based civilization had adapted to the seas? Consider this scenario. A technological species arises on land during a warm greenhouse period in Earth's past, perhaps tens or hundreds of millions of years ago, then, facing climatic disaster or overpopulation, turns to the oceans for refuge. Over generations, they evolve or engineer adaptations for aquatic life. Cities are built on the shallow seafloor, along submerged continental margins, or in submarine caves warmed by geothermal vents. Life continues there, out of sight, until eventually, some combination of environmental collapse, tectonic upheaval, or natural extinction wipes them away. Now, fast forward to today. What remains? Here's where the ocean becomes both a vault and a destroyer. Seafloor sediments accumulate slowly, millimeters per thousand years in some places, much faster in others. Over tens of millions of years, the remains of even vast structures could be deeply buried. Unlike land, where wind and weather erode surfaces, the ocean floor is a relatively stable depositional environment. But this doesn't mean it's kind to artifacts. Metals corrode in salt water. Organics decay rapidly. Most building materials crumble under deep sea pressure. And once buried, structures can be compacted, broken, or chemically altered by sedimentation. Without specific markers, like isotopic anomalies, unusual chemical signatures, or extremely durable synthetic materials, such ruins would be indistinguishable from natural rock formations. Even worse, much of the ocean floor is geologically young. As part of the tectonic cycle, oceanic crust is constantly created at mid-ocean ridges and consumed at subduction zones. The average age of the seafloor is less than 200 million years, and in many areas, much younger. That means any civilization that existed prior to that would now be lost to the mantle, recycled by Earth's relentless tectonic churn. Still, some regions might hold secrets. Large underwater plateaus, like the Kerguelen Plateau in the Indian Ocean or the Ontang Java Plateau in the Pacific, are vast, relatively stable areas of submerged land. Some of these plateaus were once above sea level before being submerged by rising seas or tectonic shifts. These drowned continents, so to speak, could have supported terrestrial or shallow water civilizations millions of years ago. Today, they lie thousands of meters beneath the surface, blanketed in sediment. Then there are the continental shelves, those shallow, submerged fringes of the continents that extend outward from the land before dropping off into the deep ocean. These areas would have been dry land during glacial periods when sea levels were lower. They are also rich in resources and would be natural locations for early civilizations. If any ancient intelligent species existed during such periods, their settlements might now be buried just offshore, under silt and sand. The challenge is that these regions are incredibly difficult to explore. Deep-sea archaeology is in its infancy. Technologies like sonar mapping, submersible drones, and deep-sea drilling are expanding our reach, but progress is slow, expensive, and limited in scope. Even our search for ancient shipwrecks is a daunting task. Imagine looking for the remnants of an entire civilization. Still, there have been hints. Anomalies. Submerged stone structures off the coasts of Japan, India, and Cuba that some interpret as ancient cities, though most scientists believe they're natural formations or more recent ruins submerged by post-ice age sea level rise. These mysteries remain unresolved, partly because we lack the data to confirm or refute them conclusively. What if, in one of these places, or 1,000 meters deeper, lies a structure not shaped by wind or water, but by intention? What if the ocean, with its silence and secrecy, is the perfect hiding place for an entire lost chapter of Earth's history? A civilization beneath the sea is not beyond the realm of scientific imagination. It requires only a willingness to reconsider the limits of biology, technology, and preservation. The ocean is vast, dark, and largely uncharted. And in its shadowed depths, time hides all things well. When we think of ancient tools, we often picture chipped stones, rusted metal blades, or pottery fragments, objects solid enough to outlast the centuries. But what happens when we imagine tools crafted not thousands, but millions, even hundreds of millions, of years ago? Could a civilization that lived in deep time have left behind tools we might recognize? And if so, could those tools have survived the immense pressures of geological time? The very concept of tools from an ancient, possibly non-human civilization forces us to expand our definitions. Tools aren't just stone hammers or bronze daggers. They are any object intentionally shaped to manipulate the environment. A tool could be a simple cutting edge or a complex energy converter. It could be mechanical, digital, biological, or something we don't even have the language to describe. The first challenge is material. Most tools made by early human civilizations were composed of perishable materials: wood, bone, leather, plant fibers. These decay quickly and rarely fossilize unless they're preserved in very specific environments like peat bogs, volcanic ash, or extremely arid deserts. Even tools made of metal, iron, copper, bronze, can corrode beyond recognition in just a few thousand years, especially when exposed to moisture and oxygen. So, if we extend this timeline to millions or tens of millions of years, what kind of materials would have the best chance of surviving? The answer lies in the extremely durable, things like stone, ceramics, and certain synthetic materials. For instance, obsidian and flint tools from early humans have lasted hundreds of thousands of years. In theory, they could survive millions. But this assumes those tools were used in the right environments, places where they could be quickly buried and shielded from weathering and tectonic activity. Now let's add an even greater stretch of time. What if a civilization existed 100 million years ago? Or 500 million? If they made stone tools and left them on a riverbank or forest floor, chances are they'd be ground to dust, buried, melted, or subducted into the Earth's mantle. The crust is not a stable surface, it recycles itself. For a tool to fossilize, it needs to fulfill several requirements: rapid burial, chemical stability, and protection from pressure and heat. It also needs to be recognizable. That last part is important, Because even if a tool-like object did survive, how would we distinguish it from a naturally fractured rock or mineral deposit? Paleontologists sometimes debate whether certain patterns in rock formations are the result of human activity or natural forces. It's hard enough to prove that a 300,000-year-old stone was intentionally knapped by a hominin. Now imagine trying to prove that an oddly shaped rock from the Devonian period was a drill bit or gear. Without context, without other supporting artifacts, we might overlook it entirely, or mistake it for coincidence. But there's another possibility. What if the tools weren't made of stone or metal at all? Advanced civilizations, especially those evolved far before us, might have developed tools from composites, polymers, biomaterials, or nanostructured elements. Some of these substances could be more resistant to decay than organic materials, but still vulnerable to geological pressures. A plastic polymer, for example, might last tens of thousands of years in the right conditions, but under heat, pressure, or microbial degradation, it could vanish long before reaching the fossil record. And then there's technology beyond tools, devices, or machines. If a past civilization used electronics or computing systems, the physical forms might have been compact, delicate, and made from specialized components. Today's microchips are made of silicon, gold, copper, and rare earth elements, but they're fragile. Exposed to weather, buried in soil, or subjected to heat, they degrade rapidly. Could anything like this fossilize? Unlikely, unless entombed rapidly and in an oxygen-free environment. Even then, recognition is another issue. Without visible indicators like etching or structural geometry, a fossilized microchip might look like an oddly shaped crystal. Without our current understanding of function and form, we might walk right past it. Another concept worth considering is bioengineered tools, devices grown rather than built. An advanced species may have used synthetic biology to create living tools, programmed organisms, or modular components that operated more like symbiotic extensions of the body. These would decay like flesh, leaving behind almost nothing, unless, somehow, their DNA or biochemical residues survived in a detectable form. It's also possible that tool use took an entirely different shape. What if their tools were forms of energy manipulation, electromagnetic, sonic, or gravitational technologies that required no traditional hardware? Such tools wouldn't leave physical remnants at all, only side effects. Perhaps subtle isotopic shifts, magnetic anomalies, or unexplained alterations in mineral structures could serve as indirect evidence. But again, without a clear baseline, we would struggle to interpret them. There's a famous saying in paleontology: absence of evidence is not evidence of absence. The fact that we haven't found ancient tools from a hypothetical pre-human civilization doesn't mean they never existed. It may simply mean we don't yet know how to look, or what to look for. And if we ever do find something, a fragment, a geometric fossil, a material anomaly, how will we know it's a tool? Will we recognize it? Or dismiss it as natural, because it doesn't match our expectations? Perhaps one day, a curious scientist will pick up a small object from a billion-year-old rock layer, feel its strange symmetry, and wonder, did someone make this? Throughout history, scattered across the layers of our planet's deep past, a peculiar class of objects has occasionally surfaced, artifacts that seem to defy the timeline we understand. These are known as OPARTs, or out-of-place artifacts. They are items found in geological contexts or archaeological layers where they shouldn't logically exist, at least not according to the conventional narrative of human history. Their very existence, if genuine, would force us to reconsider everything we think we know about the evolution of intelligence and technology on Earth. OPARTs are tantalizing. They stir the imagination. They make us wonder, could there have been forgotten civilizations before us? Advanced cultures erased by time, their legacies mistaken for anomalies or myths? Some of the most frequently cited examples include metallic spheres found in South African mines, allegedly dating back over 2 billion years. These spheres, grooved, smooth, and uniform, have been interpreted by some fringe theorists as artificial constructs. Others point to the Antikythera mechanism, a stunningly complex ancient Greek device often referred to as the world's first analog computer, found in a shipwreck dated to around 100 BC. While the Antikythera mechanism is within the known bounds of human history, it still challenges our understanding of the technological sophistication of ancient cultures. Then there are even more controversial claims: a spark plug allegedly found encased in a 500,000-year-old rock, machined metal fragments discovered in coal seams, or carvings that appear to depict modern-looking aircraft and astronauts. These are the kinds of discoveries that feed speculation and spark sensational headlines. But the mainstream scientific community remains deeply skeptical of most OOP-art claims. And for good reason. First, many so-called OOP-arts suffer from poor documentation. In numerous cases, the artifacts were removed from their context before being properly studied. Without clear, verified stratigraphic data, precise information about where and how an object was found, it becomes nearly impossible to determine its true age or origin. An object might look ancient, or be found near ancient materials, but that doesn't prove it belongs to that time. Second, some of these artifacts have been outright hoaxes. In the 19th and early 20th centuries, the public fascination with lost civilizations and biblical archaeology led to a proliferation of fake artifacts. Carved stones, mechanical parts, and supposed ancient tools were planted or misrepresented to gain fame, money, or support for specific ideological narratives. These fakes, even when debunked, continue to circulate in books, blogs, and conspiracy forums. Third, there is a powerful cognitive bias at play. Humans are naturally pattern-seeking creatures. We see order and design even when it's not there. A groove sphere might be a product of natural mineral growth and sedimentation. A seemingly artificial shape could be a coincidence of erosion, pressure, or crystal formation. And even real artifacts, like an iron hammer encased in a concretion, can be dramatically younger than the rock formations they resemble, having been enveloped in mineral deposits over a much shorter time frame than presumed. That's not to say all anomalies are explained. Some remain mysterious, not because they confirm ancient civilizations, but because our understanding of geology, metallurgy, or site history is incomplete. But science demands rigor. Extraordinary claims require extraordinary evidence. For an OOP-art to seriously challenge the scientific consensus, it would need to be found in an unambiguous, well-dated context, subjected to extensive testing, and independently verified by multiple lines of inquiry. This doesn't mean the idea of lost civilizations is off the table. It just means the evidence must match the claim. If a single microchip were found embedded in Cambrian rock, and it passed every test, the world would change overnight. But that hasn't happened. The allure of OOP-arts taps into a deeper human longing, to connect with something ancient, mysterious, and forgotten. It's the same longing that gives rise to myths. Still, the continued appearance of such anomalies, no matter how inconclusive, keeps the question alive. Even mainstream scientists recognize that the Earth is vast, the past is poorly preserved, and we haven't found everything. Most anomalies can be explained by natural processes or historical misunderstandings. But all it takes is one genuine OOP-art, confirmed and irrefutable, to rewrite our history. Until that day, OOP-arts remain artifacts not of ancient builders, but of our own curiosity, symbols of our desire to know if we truly are the first, or just the latest chapter in an older, deeper story written into the crust of the Earth. Among the many so-called out-of-place artifacts that continue to stoke debate, intrigue, and skepticism, few are as persistently enigmatic as the aluminum wedge of Ide. This object, often presented in fringe literature and mystery circles as possible evidence of ancient advanced technology, or even extraterrestrial intervention, holds a unique place in the narrative of lost civilizations and the Silurian Hypothesis. But what is it really? And does it tell us anything truly meaningful about the possibility of intelligent life before humans? The story of the aluminum wedge of Ide begins in 1973, near the town of Ide in Romania. According to the most commonly cited version of the account, workers digging a trench along the Meuse River unearthed 3 objects buried in a sandy layer about 10 meters underground. 2 of these were reportedly fossilized mastodon bones, consistent with Pleistocene megafauna. The third, however, was something very different, a small, wedge-shaped object that appeared to be made of a light metal, specifically aluminum. This immediately raised eyebrows. Aluminum is not found in metallic form in nature. It must be refined from ores such as bauxite using complex electrochemical processes, a technological capability that humanity only achieved in the 19th century. Before that, aluminum was considered more valuable than gold because of how difficult it was to isolate. So, how could an aluminum object be buried alongside bones thought to be tens of thousands, if not hundreds of thousands, of years old? Initial reports claimed the object was composed of roughly 90% aluminum, with traces of copper, zinc, lead, and other elements. Some versions of the story say the wedge was coated with a thick layer of oxide, supposedly suggesting it had aged over a significant period of time, possibly even tens of thousands of years. Its shape, triangular and mechanical looking, with what appeared to be holes or indents, fueled speculation. Was it a fragment of a gear? A foot from a spacecraft? A component from an ancient machine? Some theories, not surprisingly, leapt to the extreme. UFO enthusiasts posited that it was a landing gear from a crashed alien probe. Others claimed it was a remnant of an advanced Earth civilization that predates our own. For advocates of the Silurian Hypothesis, this was catnip, a modern material found in an ancient context, impossible to explain with current human history. Was this finally the smoking gun? But upon closer inspection, cracks in the story began to form. First, the context of the discovery is murky. Unlike rigorously documented archaeological finds, the exact location, depth, and stratigraphy of the find site were never properly recorded. There were no peer-reviewed excavations. The dating of the surrounding sediments remains vague and disputed. Without precise geological context, claims about the object's age become speculative at best. Second, a more conservative hypothesis soon emerged. Several metallurgical experts pointed out that the shape and design of the object closely resembled the bucket tooth of an industrial excavator, specifically, the kind used in heavy digging operations. These teeth are often cast from lightweight aluminum alloys to reduce strain on machinery. The oxide layer could have formed relatively quickly, especially if the object had been exposed to wet soil for decades. Furthermore, critics of the mystery note that if an excavator was used during the trench digging process, and one of its teeth broke off, it could have easily become embedded in the soft sediments, especially if nobody noticed the break at the time. Later, when workers or researchers returned to the site and found the tooth along with the bones, they may have mistakenly assumed they were contemporaneous. This is a classic case of mixed stratigraphy, where older and newer items are found in the same location but do not belong to the same time period. Additionally, the lack of peer-reviewed scientific literature supporting the wedge's ancient origin is telling. While the object is occasionally displayed in Romanian museums and frequently cited in pseudoscientific media, no rigorous archaeological or geological study has confirmed its supposed age or extraordinary origin. Still, despite the mounting mundane explanations, the aluminum wedge of Ide remains a cultural artifact of interest. Not necessarily as evidence of a prehistoric high-tech civilization, but as a symbol of how easily mystery can arise when context is lost. It illustrates how the human mind, hungry for answers and stories, can leap from a real enigma to a grand hypothesis. More importantly, it highlights the importance of scientific process when dealing with ancient anomalies. Extraordinary discoveries require stringent documentation, peer review, contextual analysis, and reproducibility. Without these, we risk being misled by errors, coincidences, or hoaxes. But at the same time, we must acknowledge that dismissing anomalies too quickly can also blind us to real discoveries that don't fit neatly into established narratives. So, does the aluminum wedge of Ide prove anything about the existence of a pre-human civilization? Not conclusively. The weight of evidence points toward a modern industrial origin, likely misplaced or misinterpreted. But its legend persists because it taps into a deeper question: could we mistake the relics of an ancient civilization for something ordinary, because we lack the context to see them clearly? It is this haunting possibility, more than the wedge itself, that continues to fuel the search for traces of civilizations lost not just in space, but in the vast, silent corridors of time. It's a question that has intrigued scientists, writers, and science fiction fans alike. Could dinosaurs have evolved intelligence? Could one of these ancient creatures, given the right evolutionary pressures and enough time, have developed not only a larger brain but the cognitive capabilities needed for tools, culture, even civilization? And if they had, could their story have risen and fallen long before ours ever began? The idea isn't just speculative fantasy. It actually has roots in real evolutionary science. Back in the 1980s, paleontologist Dale Russell, working with the National Museum of Canada, proposed a striking hypothesis. He noted that one species of dinosaur, the Trudon, had a relatively large brain for its body's size and was already showing signs of advanced neurological development. If the non-avian dinosaurs had not been wiped out 66 million years ago by the asteroid impact that triggered the Cretaceous-Paleogene extinction event, Russell argued, Trudon or something like it might have continued evolving toward higher intelligence. To illustrate this idea, he introduced the concept of the dinosauroid, a speculative, humanoid descendant of Trudon. This imagined creature had a large head, forward-facing eyes, upright posture, and even hands capable of grasping tools. In many ways, the dinosauroid looked more like a scaly alien than a dinosaur, but it was meant to make a serious point. Intelligence isn't necessarily tied to mammals, let alone primates. Under the right conditions, any vertebrate with a brain and a flexible body plan might, in theory, climb the ladder toward consciousness. Of course, not all scientists agreed with Russell's vision. Many argued that the humanoid form he imagined was too anthropocentric, too much shaped by human assumptions. There's no inherent reason why intelligence must result in a being that walks upright or resembles us. Evolution doesn't aim toward a particular goal. It responds to ecological pressures. Still, Russell's idea was provocative because it asked a bold question: if intelligence is a favorable evolutionary strategy, why should we assume it's uniquely human or even uniquely mammalian? The Trudon itself was an interesting candidate. It stood about 2 meters tall, had grasping 3-fingered hands, binocular vision, and most importantly, one of the highest encephalization quotients, a rough measure of brain size relative to body size, of any known dinosaur. Its brain-to-body ratio was comparable to that of modern birds, some of which, like crows and parrots, exhibit remarkable cognitive abilities today. So what if that trend had continued? Let's imagine an alternate Earth, one where the asteroid never hit. In this world, the dinosaurs do not vanish. Mammals remain small, marginal creatures, and birds remain just one of many evolutionary paths. Trudon and its cousins flourish in complex ecosystems. Over millions of years, they evolved greater intelligence, more refined motor control, and eventually, something we might recognize as technology. What would such a civilization look like? For one, it might not develop in the same way ours did. Dinosaurs were mostly cold-blooded, though some species may have been warm-blooded or partially endothermic. Their metabolic needs and social behaviors might have led them to favor different environmental niches. Perhaps their cities would be subterranean to manage temperature. Perhaps they'd rely on biological engineering long before metallurgy. Maybe they'd develop communication through color change, chemical signals, or even infrasonic sound. And their tools? Not necessarily hammers and spears. A species with claws and prehensile digits might invent different categories of instruments. A civilization based on reptilian neurobiology could think in patterns or intervals we can't comprehend, perhaps even relying on instincts shaped by predator-prey dynamics or migratory rhythms. Could they have discovered fire? That's debatable. Many dinosaurs, especially theropods, didn't live in forested regions where fire might occur naturally. But if one branch evolved in a fire-prone habitat and learned to control it, that could change everything. Fire leads to cooking, metallurgy, industry. If not fire, maybe they'd harness geothermal vents, bioelectrical energy, or even piezoelectric crystals, using Earth's vibrations to store and transfer energy. If such a civilization ever existed, and it fell, as most civilizations eventually do, what would it leave behind? This brings us full circle to the Silurian hypothesis. The fossil record has huge gaps. Entire species are known from just a tooth or a single bone. If a reptilian civilization had arisen 70 million years ago, it might have been erased not just by time, but by tectonics, erosion, and the recycling of Earth's crust. The deeper in time we go, the harder it is to find even the remains of abundant life, let alone a small, intelligent lineage that may have built tools or machines. And there's one more complication. What if they didn't fossilize in ways we'd recognize? A stone carving might survive, but what if they built with organic materials, or settled regions that are now underwater or subducted? What if their most lasting legacies were chemical, alterations in the carbon cycle, unexplained isotopic shifts, or trace elements in rock strata? These are the types of anomalies that the Silurian hypothesis dares us to take seriously. Not because we have clear proof of dinosaur civilizations, but because the absence of evidence, especially across millions of years, is not evidence of absence. To this day, no fossils have been found that show signs of tool use or culture in non-avian dinosaurs. But absence doesn't rule out the possibility. It only tells us that if such a species did exist, its story ended long before ours began, leaving barely a whisper in the geological record. And yet, we still wonder. In every lizard's eye and every ancient fossil jaw, we glimpse an alternate path not taken. A path where the age of reptiles never ended, but transformed into something intelligent, social, and perhaps even self-aware. It's one thing to imagine a past civilization that built cities, crafted tools, or even developed agriculture. But what if a species that lived long before humans didn't just reach the level of basic technology, but instead climbed all the way to the mountaintops of science? What if they didn't just invent the wheel or the plow, but uncovered the laws of motion, the nature of the atom, or even the structure of space and time? Could a civilization in Earth's deep past have discovered physics? It sounds impossible. After all, we think of ourselves as the peak of intellectual evolution on this planet. We split the atom. We built particle accelerators. We stare into the birth of the universe with radio telescopes and launch spacecraft into the outer solar system. But the Silurian hypothesis forces us to ask uncomfortable questions, not just about biology or archaeology, but about knowledge itself. If intelligence once emerged and advanced on Earth before us, how far could it have gone? Could a pre-human civilization have developed a science as deep and abstract as our own? To consider this, we must first understand how science emerges. Physics, like all knowledge systems, begins with observation. The earliest humans watched the sky, the stars, the seasons. They noticed patterns, how objects fall, how shadows move, how fire behaves. These observations, formalized and refined, eventually became principles. And over millennia, those principles evolved into models, equations, and unifying theories. It was a slow and fragile process, dependent on literacy, record-keeping, tools, and institutions that could preserve ideas across generations. Now imagine a different species, perhaps one that lived 100 million years ago, following a similar path. If they reached a level of technological sophistication equivalent to the Industrial Revolution, they might have developed mechanics, thermodynamics, and electromagnetism. If they advanced even further, perhaps over a span of tens of thousands of years, they could have progressed into quantum theory, particle physics, and general relativity. The nature of these discoveries doesn't rely on being human. They are universal truths waiting to be uncovered by any mind curious and capable enough to see the patterns. Could they have built telescopes to observe the stars? Instruments to measure radio waves? Laboratories to explore atoms and energy? If so, where are the remnants? That's where the mystery deepens. Most tools of modern science, our electronics, sensors, detectors, are fragile, small, and built from materials that decay quickly over time. A particle accelerator made of steel and silicon would not last millions of years unless buried in a geologically stable location, protected from erosion, tectonic shifts, and weather. Even the most massive structures, like our hydroelectric dams or space telescopes, would vanish under the grinding wheel of time. Unless we happen to find them in a rare state of preservation, their traces would be indistinguishable from natural formations. But there's another possibility, one even more haunting. If such a civilization reached the heights of physics, could they have also reached the ability to hide themselves? Perhaps deliberately? If they studied quantum entanglement, they may have discovered means of instantaneous communication across distance, technologies that left no physical artifacts. If they explored antimatter or vacuum energy, they might have used power sources that didn't require vast infrastructure or combustion, leaving behind only slight isotopic anomalies or unexplained thermodynamic signatures in the geological record. If they experimented with black holes, gravity waves, or high-energy particles, they might have built tools in space, far from Earth's surface, where no sedimentary layer could trap their traces. And here's another chilling question. Could they have encoded their knowledge in ways we haven't yet recognized? We assume science is preserved through language, symbols, and mathematical notation. But what if a previous civilization inscribed its findings in DNA? Or in crystalline patterns? Or in information embedded in quantum states or neutrino pulses, forms of data invisible to our conventional senses? Or what if they didn't want to be remembered? It's possible that any species which survives long enough to master physics also understands its own fragility. They may witness the consequences of unrestrained power, climate collapse, weapons of mass destruction, or ecological devastation. Knowing this, perhaps they made the ultimate choice, not to leave behind monuments, but to vanish silently, leaving as little evidence as possible. A deliberate erasure. That idea may seem fantastical, but it's rooted in a simple truth: the universe does not care whether knowledge survives. Only those who use it, and those who inherit it, can carry it forward. Could a species have understood quantum mechanics millions of years before us? Could they have grasped the curvature of spacetime, built theories of the multiverse, or calculated the entropy of black holes? Theoretically, yes. Intelligence and science are not uniquely human phenomena. They are outcomes of evolutionary and cognitive complexity. They are pathways available to any species capable of abstraction, logic, and sustained inquiry. And if that species once walked the Earth, if it built observatories, pondered particle wave duality, or stared at distant galaxies with instruments long turned to dust, then their silence is all the more profound. Because it means we are not the first to ask what the universe is made of. And perhaps not the first to disappear after finding out. When we think of signs of advanced civilization, few are as dramatic, or as unmistakable, as the harnessing of nuclear energy. Nuclear technology is one of the clearest dividing lines between a pre-industrial and post-industrial society. It requires not only complex knowledge of physics, but precise engineering, rare materials, and a deep understanding of both energy and risk. So, if a pre-human civilization on Earth had ever reached a comparable level of technological sophistication, one of the most compelling avenues for discovering them would be to look for signs of ancient nuclear activity. But here's the twist: Earth already has known examples of nuclear reactors from the distant past. Only they weren't built by intelligent life. Or so we think. In the 1970s, scientists discovered something extraordinary in a uranium mine in Oklo, Gabon, in West Africa. There, buried deep underground, they found a series of natural nuclear fission reactors. Reactors that had been active some 2 billion years ago. Yes, you read that correctly. Earth naturally built and operated nuclear reactors long before humans walked the planet. The Oklo reactors worked because the concentration of uranium-235 in natural uranium was once much higher than it is today. Combined with the presence of water acting as a moderator, and the specific geometry of the uranium deposits, this created the ideal conditions for spontaneous, sustained nuclear fission. These reactors ran intermittently over hundreds of thousands of years, creating isotopic residues and trace elements nearly identical to those produced by modern nuclear facilities. Why does this matter? Because it tells us something crucial: nature can mimic the fingerprints of civilization. If we stumbled upon Oklo today without knowing its origin, we might suspect it was artificial. And this creates a challenge. If a past civilization had created a real, artificial nuclear reactor millions of years ago, Could we distinguish its remnants from a natural anomaly? Let's explore that. Modern nuclear reactors produce specific isotopes, particularly cesium-137, strontium-90, and iodine-131, alongside plutonium and various transuranic elements. Some of these decay quickly, but others, like plutonium-239, can persist for tens of thousands of years. Over millions of years, most short-lived isotopes would vanish, but their daughter products might remain. These decay chains leave a chemical trail, almost like a fossil, but radioactive. In theory, if we found a concentration of unusual isotopes, especially those not typically found in natural uranium decay chains, we might suspect artificial nuclear activity. For example, the presence of certain synthetic isotopes in rock layers millions of years old would be incredibly difficult to explain through natural processes alone. But again, there's the geological filter to contend with. The Earth's crust is dynamic. It shifts, melts, erodes, and recycles. A reactor built on the surface millions of years ago would likely have been eroded down to nothing. One buried underground might be better preserved, but would still be vulnerable to mineral migration, chemical leaching, or tectonic activity. The isotopic signatures could disperse, become diluted, or be misinterpreted as anomalies in natural or formations. Still, scientists have begun looking for unexpected nuclear isotopes in ancient rock layers, particularly around boundary layers associated with dramatic climate shifts or unexplained heat pulses. The idea is not to prove ancient reactors existed, but to recognize that if something anomalous were ever found, something that doesn't fit natural uranium decay, and doesn't match known astrophysical processes, it could point to something else. Something artificial. Another clue could come from glass, specifically, trinitite, the glassy substance formed when sand melts in the intense heat of a nuclear explosion. On modern Earth, trinitite is a legacy of the first atomic bomb tests. If similar glass were found in very old strata, far older than human civilization, it would be difficult to explain naturally. Volcanic glass has its own unique chemical and structural properties, distinguishable from nuclear vitrification. Then there's the idea of radiation damage in crystals. When high-energy radiation passes through certain minerals, it leaves a signature, microscopic tracks, discoloration, or rearranged crystal lattices. Some of these, called fission tracks, can be dated. If we were to discover minerals with unusual fission track densities in deep-time formations, especially in places lacking any natural uranium concentrations, it might hint at artificial nuclear processes. And we haven't even touched on nuclear waste. A truly advanced civilization would need to manage its radioactive byproducts. Would they bury them? Launch them into space? Encapsulate them in synthetic glass or deep earth containers? If we ever uncovered something like a containment chamber or signs of nuclear vitrification deep in the crust, it could be the fossilized scar of an ancient civilization's power source, or its demise. Of course, mainstream science has yet to find such conclusive evidence. The burden of proof remains incredibly high. As with all facets of the Silurian hypothesis, we're not claiming proof, we're asking what would the evidence look like if it existed, and how long could it survive? One thing is clear, the tools of nuclear physics leave behind unusual and durable fingerprints. Radiation changes matter. It mutates atoms. It creates new elements. And while the Earth is adept at burying its past, it's not perfect. Some secrets might still be hiding, waiting for the right set of eyes and the right questions. So if we ever find ancient rock bearing signs of radiation that don't belong, or isotopes that have no natural explanation, we'll have to ask, was this nature, or was it a memory from a civilization long gone, whose science rivaled or even exceeded our own? When we think of the artifacts civilizations leave behind, we imagine stone monuments, rusted tools, lost cities, and broken satellites, physical remnants carved into the world. But what if an ancient civilization didn't rely on stone or steel to preserve its knowledge? What if, instead, it chose biology, life itself, as the medium for its message? This is the haunting speculation behind the idea of hidden messages in DNA. It suggests that the most enduring record of an intelligent civilization may not be buried in sediment or fossilized in rock, but silently replicated in every living cell, written into the genome of Earth's creatures, hiding in plain sight. The idea isn't as far-fetched as it sounds. DNA is one of the most stable, long-term information storage systems known to science. With just 4 chemical bases, adenine, A, thymine, T, cytosine, C, and guanine, G, it encodes instructions for building and sustaining life. But these same bases can also be arranged to store arbitrary data, numbers, letters, images, and even sound. In fact, modern scientists have already demonstrated the ability to store books, videos, and even computer software within DNA molecules. It's incredibly compact and, under the right conditions, remarkably durable, far more so than magnetic tapes, hard drives, or paper. Some DNA recovered from permafrost or amber has lasted hundreds of thousands, even millions of years. So what if a long-lost civilization, knowing the fragility of physical artifacts, chose to store its legacy in the very language of life? Perhaps they encoded mathematical constants, chemical blueprints, or cosmological models into the junk DNA, regions of some long-extinct species. Or maybe they implanted a self-replicating genetic message, like a biological Rosetta Stone, that would persist and spread across generations, embedding itself in ecosystems the way a virus does. Unlike stone or plastic, this method wouldn't depend on being found in one place. It would travel with life itself. This line of thinking also intersects with another profound mystery, the origin of life. Where did DNA come from in the first place? What if it was seeded here, not by chance chemistry, but by design? The idea of directed panspermia, that life on Earth may have been seeded deliberately by an advanced civilization, is controversial but not entirely dismissed in theoretical circles. Nobel laureate Francis Crick, co-discoverer of the structure of DNA, once suggested that Earth's earliest microbes might have been sent here intentionally in a spacecraft, engineered to spark a biosphere. If this were true, the seeding civilization may have left its signature not in metal plates or coded beacons, but within the genome itself. Imagine, you decode a stretch of ancient DNA and discover something strange, not just biology, but syntax. A repeating pattern that corresponds to prime numbers. A molecular structure that encodes the digits of pi. A protein sequence that maps to the periodic table. These would not occur naturally. There would be intelligent design in the truest, scientific sense, not theological, but technological. There's also the possibility that life on Earth was subtly programmed to evolve a certain way. Evolution is famously unpredictable, yet convergent evolution, where different species independently evolve similar traits, suggests there are deep patterns in biology. What if those patterns were preceded? What if the entire arc of evolution was nudged toward the eventual rise of intelligence, not once, but cyclically? Even more mind-bending is the idea that a previous civilization embedded messages intended for us, knowing we might one day sequence genomes. Just as we send digital records into space aboard spacecraft like Voyager, could they have left behind a biological time capsule, counting on the idea that someday, somewhere, a species would become curious enough to read it? Of course, we must tread carefully here. The danger of anthropocentric projection, the tendency to see intention where there is none, is real. DNA is full of complex, repetitive, and poorly understood sequences. Many regions labeled as junk are simply unexplored, not useless. Patterns may emerge purely by coincidence. Our brains are wired to find meaning, even where none exists. Any discovery would have to be rigorously validated, replicated, and shown to be statistically impossible through chance or biology alone. To date, no such encoded message has been found. No prime numbers in our genes. No cosmic maps in bacterial chromosomes. But absence of evidence is not evidence of absence, especially when we've only just begun to understand the full depths of the genome. And the implications are staggering. If a message were found, authentic and verifiable, it would rewrite our understanding of Earth's history. It would mean we are not the first to rise, not the first to think, not the first to ask what the stars are made of. It would mean we carry the legacy of others not just in myth, but in our very cells. So we continue to search. In data. In fossils. In isotopes. And now, perhaps, in the very code of life. Because the past may not be lost, it may be alive inside us, quietly waiting to be read. Why would a civilization, especially one advanced enough to manipulate DNA, split atoms, or grasp the architecture of the universe, simply vanish? If such a species once thrived on Earth long before humans, why would there be no obvious monuments, no galactic beacons, no trace etched across the planet for us to find? This question strikes at the heart of the Silurian hypothesis. It isn't just a matter of where the evidence might be, but why there might be so little in the first place. And to understand that, we must confront a grim possibility. Perhaps they disappeared not by accident, but by consequence. Let's begin with the most obvious theory, self-destruction. History, even in our own short span, offers no shortage of warnings. The very tools we invent to improve our lives often carry the seeds of our undoing. Nuclear energy brings both electricity and extinction. Chemical innovation can yield medicines, or poisons. Artificial intelligence might help solve complex problems, or render entire populations obsolete. If we, in just a few hundred years, can teeter so close to self-annihilation, imagine a civilization that had a million-year head start. The more advanced a species becomes, the more powerful its technology, and the more devastating its mistakes. A pre-human civilization may have reached a point where it could reshape the planet, but also rupture it. Perhaps they triggered a global ecological collapse, poisoning the oceans, destabilizing the climate, or even causing a mass extinction. Their industry could have burned so hot and so fast that it consumed the very environment that sustained them. If this happened tens of millions of years ago, the layers of sediment we now examine for fossils might be the scar tissue of their fall, a spike in carbon, a drop in biodiversity, a sudden thermal event with no clear cause. But collapse doesn't always come in an explosion. Sometimes it creeps in through resource exhaustion. Civilizations grow on energy. Food, water, metals, fuels, these are the arteries of technological progress. If a civilization drains its aquifers, strips its forests, mines out its rare earths, or overdraws its energy reserves, it begins to collapse from within. Infrastructure breaks down. Populations fragment. Knowledge is lost. Collapse might come gradually over thousands of years, long enough to fade from memory, short enough to vanish from the geologic record. And yet not all disappearances must come from failure. What if a civilization chose to vanish? Imagine a species that reached enlightenment, not just intellectually, but existentially. They may have seen the trajectory of all civilizations as inherently cyclical: rise, overreach, and fall. Perhaps, foreseeing their own collapse, they decided to step away. Not to die, but to leave the material world. They may have uploaded their consciousness into biosystems, or transitioned into synthetic life, or even departed Earth entirely. This introduces the theory of voluntary vanishing. It suggests that a species advanced enough to become post-biological, living as information, energy, or quantum patterns, might have no need for buildings, cities, or any of the markers we associate with civilization. Their presence would leave no footprint in stone, no fossil in clay. They could exist within the quantum foam, within black holes, or scattered across the electromagnetic spectrum, silent, invisible, eternal. Or perhaps they practiced deliberate erasure. Maybe they wiped away all evidence of their existence, either to prevent interference with future species, or as an act of humility. Think of it as the cosmic equivalent of the Prime Directive. Let others find their own way. Do not influence the next. If such a civilization existed, they may have viewed their departure as a cleansing, leaving Earth untouched for the next intelligence to bloom. There's also the possibility of intervention or migration. Maybe they didn't vanish but were taken, or chose to leave. Perhaps they discovered a method of escaping the confines of a dying Earth and migrated to space, other dimensions, or distant worlds. Their legacy wouldn't be underground, but off-world. We might be looking in the wrong place, digging in the dirt, when their footprints lead skyward. And finally, consider the sobering idea that even success leads to silence. A species that solves all its problems may lose its drive to change, to expand, to leave behind physical marks. Comfort breeds stasis. Innovation wanes. Without struggle, without entropy, without a reason to push boundaries, a civilization might stagnate, fade, and quietly disappear, content, but forgotten. All of these theories, self-destruction, exhaustion, transcendence, withdrawal, are haunting reflections of our own possible futures. They aren't just about some distant past. They're mirrors. The Silurian Hypothesis forces us to look not only backward, but inward and forward, too. If others came before us, then we are merely the latest chapter in a longer story, one that may repeat, one that may echo, or one that may end the same way. So why would a civilization disappear? Maybe because every civilization eventually must. Would a past civilization want to be found? It's a deceptively simple question that opens a deep well of speculation, one that stretches the Silurian Hypothesis beyond geology and into psychology, ethics, and even metaphysics. It forces us to ask not only whether traces of an ancient civilization could remain, but whether such a civilization would intend for us to find them, or whether, for reasons we may not yet comprehend, they would choose to hide everything. There's a powerful precedent for this idea in our own species. When we look to the stars and consider broadcasting messages to alien civilizations, we often argue about the wisdom of doing so. Should we announce our presence to the cosmos, knowing nothing about who, or what, might be listening? Or should we remain silent, out of caution or humility? That debate mirrors a similar one about the past. If a civilization existed on Earth millions of years ago, it's entirely reasonable to consider that they might have grappled with the same dilemma. And they may have concluded that silence was safer. Perhaps they foresaw that the rise of another intelligent species was inevitable, that given enough time, another creature would look up at the stars, split atoms, and ask the same questions. If they believed in preserving the autonomy of future civilizations, they might have decided to erase all clues, to ensure that no guiding hand interfered. It's not hard to imagine a society advanced enough to master genetics, planetary systems, or even quantum fields choosing to step quietly into the void, leaving no trace behind out of a kind of ethical restraint. A deliberate vanishing act in the name of cosmic non-interference. But there's also a darker possibility. What if they hid themselves not to protect us, but to protect themselves? A civilization that once faced near extinction, whether through war, climate disaster, or artificial intelligence, might conclude that discovery equals danger. If they witnessed what happens when knowledge falls into the wrong hands, they might have buried or scrubbed every trace of themselves, worried that future civilizations would dig up tools not meant for them. Tools too powerful, too volatile. Knowledge that, once rediscovered, might lead to the same mistakes, to the same fall. So they covered their tracks not out of kindness, but out of fear. And they may have been thorough. Think for a moment about our own capabilities today. We are just beginning to explore synthetic biology, gene editing, and quantum computing. Already, we can manipulate the fabric of life, process data at unimaginable speeds, and control matter at the atomic level. Now project that forward a few million years. A civilization with that kind of technological head start could erase itself in ways we cannot yet imagine. Not just destroying records, but rewriting sedimentary layers, engineering planetary systems to reset, or even creating a kind of planetary amnesia, a deliberate blurring of historical data. Could they have edited the DNA of surviving species to remove any traces of their own origin? Could they have triggered tectonic or volcanic events to collapse their cities into the sea? Could they have developed nanotechnology capable of deconstructing their machines into dust, leaving nothing behind? If we can already imagine technologies that dissolve plastics, decarbonize landscapes, and terraform environments, it is not a stretch to imagine a species capable of global self-erasure. There's even a possibility rooted in culture, shame. What if their civilization ended badly? If they saw their legacy as a failure, they might have chosen not to be remembered. Every civilization wants to be seen as noble, just, enlightened. But if their end was cruel or cowardly, they may have sought to bury the evidence. The geological silence, then, might not just be due to time, it might be the result of deliberate collective forgetting. And there's the strangest possibility of all: they're still here. Not in the literal sense of roaming the forests or living in lost cities, but embedded in our systems, our ecosystems, or even our biology. If a civilization had transcended the need for form, if it existed now as distributed consciousness or as a networked intelligence within the biosphere, it might hide by blending in, watching, waiting, guiding subtly, or simply observing without interfering. It's a strange, unsettling idea that our world might still carry their presence, hidden not because they feared us, but because they chose to let us evolve alone. So would they want to be found? If they believed in ethical silence, the answer might be no. If they feared misuse of their technology, the answer might be no. If they regretted their past, the answer might be no. If they're still here, maybe we'll never get the chance to ask. But if there's even the smallest part of them, some data fragment, some geological anomaly, some cryptic code hidden in life itself, waiting to be discovered, then perhaps the answer isn't a clear yes or no. Perhaps they left the choice to us. To search. To question. To understand. Or to let the past remain buried, unfound, but never quite forgotten. We live in a time where scientists scour the surface of Mars for evidence of water, microbial life, or ancient atmospheric changes. We send rovers to dig, drones to fly, and satellites to scan every contour, all in pursuit of one profound goal: to find out if Mars ever hosted life, or even a civilization. We analyze distant exoplanets for chemical imbalances in their atmospheres that could hint at industry. We listen for radio signals across the cosmos and ponder what alien technosignatures might look like. But in all this searching, one question lingers quietly, awkwardly, right beneath our feet. Why don't we apply the same scrutiny to Earth? This is where the bold and relatively young field of planetary archaeology enters the picture, not focused on Mars, not on Europa, not even on distant Kepler worlds, but on our own planet. The core idea is simple yet revolutionary: treat Earth as if it were an alien world. Examine it with the same forensic curiosity and skepticism we reserve for places beyond our sky. After all, if we're willing to dig into Martian soil to look for past civilizations, why wouldn't we dig into Earth's ancient layers with the same intensity? It's not that planetary archaeology hasn't begun, it has, but only in fragments. Traditional archaeology explores human-made structures and artifacts within the relatively recent past, going back tens of thousands of years. But that barely scratches the surface of Earth's 4.5 billion-year timeline. Planetary archaeology proposes looking at the entire geological record with a new question in mind: what if we are not the first? We already possess the tools. Satellite imaging can detect unusual patterns in terrain, linear structures, grids, or symmetry that nature doesn't tend to produce. Deep core drilling projects retrieve ancient sediment and ice layers that could contain microscopic remnants of past activity. Geochemical assays allow us to detect even trace levels of synthetic isotopes, industrial chemicals, and rare elements. With these techniques, we already know how to spot technosignatures on exoplanets. We just haven't focused those efforts inward, toward our own deep past. Imagine re-examining Earth with alien eyes. You're an interstellar archaeologist arriving on this blue-green world. You note massive biodiversity, a layered crust of history, and a current industrial civilization, but what of its deeper past? You begin probing the crust for signs of earlier intelligence, anomalous isotopic ratios, unexplained climate events, layers of synthetic materials, sudden shifts in atmospheric chemistry that can't be accounted for by volcanoes or meteor impacts. This, in essence, is the mindset planetary archaeology asks us to adopt. One example might be a re-evaluation of the Paleocene-Eocene thermal maximum we previously discussed. Could such a dramatic and abrupt warming event have been triggered not by a purely natural process, but by widespread industrial emissions from a prior civilization? Similarly, could isolated layers rich in metals like palladium, iridium, or refined aluminum suggest mining or manufacturing on a vast scale? And here's a fascinating twist. Some planetary scientists argue that if we found the same chemical and atmospheric anomalies on another planet, let's say methane spikes, CO2 surges, or artificial isotopes, we would immediately suspect industrial activity. But when we see them in Earth's deep past, we rarely jump to that conclusion. Why? Because we assume humans are the only intelligent civilization Earth has ever produced. That assumption is a bias, and planetary archaeology seeks to challenge it. This discipline would also involve a cross-disciplinary alliance unlike anything in science today. Geologists, paleontologists, nuclear physicists, chemists, archaeologists, climatologists, and even computer scientists would need to come together to form a picture that spans eons, not centuries. It would require us to reconstruct not only what Earth looked like, but what might have been possible for any previous species, how they might have lived, what they could have built, and how they might have vanished. And then there's the question of intent. If such a civilization once existed, and if they did indeed choose to vanish quietly or erase themselves, we would be hunting traces they deliberately tried to obscure. That's not unlike cryptographers trying to decode a cipher written to be forgotten. In this way, planetary archaeology would resemble not just science, but detective work, following a cold case through time, seeking a suspect who left behind no obvious fingerprints. But why now? Why is planetary archaeology becoming relevant today? Because we've reached a point where human civilization is altering Earth in ways that will be detectable millions of years from now. The Anthropocene, the proposed geological epoch defined by human impact, is laying down a technosignature that future archaeologists, whether human or otherwise, could study long after we're gone. Plastics embedded in the sediment, isotopes from nuclear tests, industrial metal concentrations, atmospheric chemistry changes, all are being encoded into the geological record as we speak. In other words, we are writing our own layer into the stone library of Earth. If we know what our own civilization looks like in the rock, then we also know what to look for if another once existed. This isn't science fiction, it's a call to expand our perspective. It asks us to stop assuming that humanity is the pinnacle of Earth's story and to start considering that we may be one of several high points along a very ancient and very complex timeline. It invites us to dig deeper, not just into the ground, but into the past itself, with a fresh hypothesis, a skeptical mind, and the humility to admit, we may not be the first. We may only be the latest. If there's one thing we've learned from studying our own civilizations, it's this: memory is fragile. Even the most advanced cultures are vulnerable to forgetting, not just myths and fables, but whole cities, peoples, languages, and technologies. So what happens when memory stretches not across centuries, but across millions of years? That's the chilling foundation of what some call the Great Forgetting, the idea that even if an advanced civilization once existed on Earth, time alone could have buried it beyond recall. To understand the depth of this, we don't need to look back to the age of dinosaurs. We can start just a few thousand years ago. Consider how little we know about some of the earliest human civilizations. The Indus Valley Civilization, once thriving along the banks of the Sarasvati and Indus rivers, built cities with advanced drainage systems and standardized weights, but we still cannot read their script. Their language is a mystery. Their literature, if it existed, is gone. We only began to rediscover their cities in the 20th century, and even now, large parts remain unexplored. And that's from a civilization that may be only 4,000 years old. Go back a few thousand more years, and the picture becomes foggier. What exactly happened during the Neolithic Revolution, this shift from hunter-gatherers to settled farming? Who built the megalithic sites scattered across the globe, some of which predate known civilizations by millennia? Sites like Göbekli Tepe in Turkey, constructed nearly 12,000 years ago, suggest complex societies far earlier than we once believed. And yet, we have no records, no clear answers, only stones arranged in perplexing formations, eroded by time. Now stretch that forgetting back millions of years. Human writing has existed for barely 5,000 years. Our most durable records, books, websites, digital storage, are alarmingly fragile. Paper decays in decades. Hard drives fail in less than a century. Stone carvings can erode in a few thousand years, depending on the climate. Without preservation, most human records would vanish in a geological blink. If an event wiped out humanity today, how much of our knowledge would survive even 10,000 years, let alone 10 million? The Library of Alexandria, once the greatest repository of knowledge in the ancient world, was destroyed multiple times by fire and conflict. Countless texts, histories, philosophies, and discoveries were lost forever. And that happened in a world still filled with people, still able to speak, remember, and rebuild. A truly global catastrophe, one that removed the knowers themselves, would obliterate memory at its roots. This is the terrifying mechanism of the great forgetting, the absence of minds to remember, not just the absence of records. Language dies when the last speaker dies. Oral histories vanish when the last elder falls silent. And civilizations that do not encode their knowledge into structures that can resist time and entropy may leave behind nothing but ambiguous traces, a strangely cut rock, an odd metal inclusion, an unexplained anomaly in the soil. Without context, even advanced artifacts become meaningless. A microchip unearthed in 50 million years would likely be mistaken for a mineral fragment. A synthetic polymer, reduced to molecules, would blend in with sediment. And without a living intelligence to interpret, to question, to make sense, it all dissolves into noise. There's also the sobering fact that even within a single culture, forgetting is routine. Stories are revised. Documents are lost. Histories are rewritten. Multiply that forgetting across geological timescales and tectonic upheaval, and the odds of remembering anything from a lost civilization, especially one that predated humans, becomes vanishingly small. In the context of the Silurian Hypothesis, the great forgetting becomes both a filter and a paradox. It filters out the evidence we might hope to find. But it also reminds us that the absence of evidence is not evidence of absence. Our failure to uncover signs of a past civilization may not mean there was none, it may simply reflect the inevitable decay of memory in deep time. And what of prehistory? Prehistory is the vast canvas of time before written records. It's estimated that 99.9% of human existence lies within this forgotten space. Everything we know about early Homo sapiens, Neanderthals, Denisovans, and even more ancient hominins comes from scattered bones, stone tools, cave art, and genetic hints. Prehistory is not a timeline, it's a fog. If this is how little we know about our own species in the recent past, what chance do we have of identifying a completely different species that may have risen and fallen 100 million years ago? We may be walking on the graves of entire civilizations, utterly unaware. Their bones have crumbled to dust. Their machines corroded to atoms. Their thoughts, dreams, and discoveries lost to the long sleep of Earth. All that remains is silence, and the questions we dare to ask in the face of it. What did we forget? What have we never known? And most importantly, what will those who come after us remember of us, when we too are gone? If civilization can fall, then why not rise again? That's the profound question at the heart of cyclical models of history, an idea that has echoed across myth, philosophy, and even science for thousands of years. Could civilization on Earth have restarted multiple times? Could our own age of steel and silicon be just one in a long, forgotten cycle of birth, collapse, and rebirth? When we examine the timeline of Earth, we find a story not of constant progress, but of starts and stops. Mass extinctions reset the biosphere. Climate shifts redraw the limits of habitability. Asteroid strikes, supervolcanoes, and ice ages shatter stability and erase entire ecosystems. Evolution itself is not a straight line, but a dance: advance, retreat, transform. What if civilization follows the same rhythm? In the Silurian Hypothesis, this question becomes especially potent. If intelligent life evolved before humans, millions or even hundreds of millions of years ago, it may have reached its zenith, collapsed, and then restarted. Not just once, but perhaps many times, in layers so deep we can no longer distinguish one from another. Like pages in a burned book, the details are lost, but the ashes remain. Let's begin with the idea of civilizational memory loss. After a global collapse, survivors may retreat into small, scattered groups, hunter-gatherers, isolated agriculturalists, or oceanic islanders. With time, knowledge becomes fragmented. Scientific understanding fades into myth. Electricity becomes legend. Eventually, even the memory of memory disappears. By the time a new civilization rises, it has no idea there was ever one before. Then there is the principle of recurrence through necessity. Civilization, once possible, may be inevitable under the right conditions. Given access to fire, tools, surplus food, and time to think, intelligence tends toward technology. Even if all were lost, as long as Earth remains habitable, new minds may once again build, question, and reach upward. This creates the possibility of civilizational cycles, not a single climb to greatness, but many, each rising from the ruins of the last. We might even consider geographic isolation as a key. Civilization doesn't need to evolve globally to count. A localized advanced society, say, on an ancient supercontinent like Gondwana, could flourish, collapse, and vanish without affecting distant ecosystems. When tectonic plates scatter and reform, their memory may be buried under oceans or thrust into mountain ranges. Each new civilization could arise in a different place, at a different time, unaware that anything came before. This brings us to cultural bottlenecks, moments where global catastrophe nearly wipes out humanity, or whatever dominant species exists at the time. Scientists have found evidence of such bottlenecks in our own genetic history. Around 70,000 years ago, the human population may have dropped to as few as 1,000 breeding pairs after the Toba supervolcano eruption. If that eruption had been slightly more severe, modern humans might never have risen. And if we had already been advanced at that point, we might have forgotten everything. The next iteration could have started from scratch, without even knowing it. There is also the disturbing possibility that each cycle forgets faster. As we move into digital data, cloud storage, and ephemeral formats, the physical record of our civilization becomes less durable. Stone tablets can last thousands of years. Papyrus, centuries. A solid-state hard drive? Maybe a few decades if you're lucky. What happens when a collapse takes out the electric grid? Our knowledge disappears in an instant, erased not by fire, but by silence. Future species might find fragments but lack the means to read them. The entire digital age could become a ghost, irretrievable without its context. But perhaps the most fascinating aspect of this theory is that civilization itself may be natural, not an aberration of evolution, but its highest expression. In this view, intelligence is not rare, but recurring. Life pushes toward complexity. Complexity gives rise to minds. Minds create civilization. Civilization overreaches and collapses. And then, in the quiet aftermath, the process begins again. It's not a tragedy, it's a pattern. A planetary heartbeat. We may be living in the latest iteration of that pattern. We are told that we are the first, that no other species has built what we've built. But that confidence rests on an assumption, that we would know if there had been others. Yet as we've seen, time is the greatest eraser. Earth is not a museum, it is a recycling engine. Mountains are ground down. Oceans rise and fall. Continents drift. And memory, without a steward, vanishes. What if there were once others? Civilizations of reptilian thinkers, ocean dwellers, insect engineers, or even mammalian cultures that rose and fell during warm eons between ice ages. What if they, like us, looked to the stars and asked if they were alone, never knowing they were part of a cycle much older than themselves? And if it's happened before, it may happen again. Our own civilization is not guaranteed permanence. Whether through ecological collapse, war, technological disaster, or cosmic accident, we may join the forgotten. But if history is cyclical, then this is not the end, it is simply another beginning. A new rise will come. A new mind will build. A new species will inherit the ashes of our story, whether they know it or not. And they, too, will wonder. When we look up at the night sky, two planets stand out, not because they're the most distant, but because they are the most familiar. Mars and Venus, Earth's next-door neighbors in the solar system, have long been objects of fascination. They sit within what we call the habitable zone, the sweet spot around a star where liquid water could, at least theoretically, exist. But beyond their scientific allure, there's a deeper, more unsettling question that has only recently started to creep into serious conversation. Could Mars or Venus have once hosted civilizations of their own? And more provocatively, if they did, what might that say about Earth? Let's start with Mars, the red planet. Today it's a barren, dusty world, scarred by craters and whispering thin traces of atmosphere. But billions of years ago, it may have been radically different. Geological evidence points to ancient rivers, lakes, and possibly even oceans. Orbital satellites have photographed dried riverbeds, floodplains, and deltas, features that, on Earth, are always associated with liquid water. Mars also has minerals that typically form in the presence of water, including clays and sulfates. And the Mars rovers have confirmed that the planet was once warmer, wetter, and potentially more Earth-like than it is today. All of this makes Mars a prime candidate in the search for past life. But what if life didn't just evolve there? What if it advanced? Imagine a Martian civilization rising during this warm, wet period. Perhaps it emerged in isolated pockets, along coastlines, in underground aquifers, or near geothermal vents. Perhaps it developed tools, agriculture, or even rudimentary technology. But as Mars lost its magnetic field, its atmosphere began to erode. Solar radiation stripped it of its warmth, and the surface froze. Without atmospheric pressure, surface water boiled away or seeped underground. And any Martian civilization, if it existed, would have faced a mounting environmental catastrophe. Forced to retreat, adapt, or perish. Could a dying Martian society have attempted to preserve itself? Burrowed deep underground? Fled into space? Some have speculated, only semi-seriously, that life on Earth could be a result of Martian seeding, whether by natural panspermia or by design. In that telling, we are not Earth's first civilization at all. We are Martians, surviving on a second world, starting again from scratch. Now shift focus to Venus, Earth's twisted twin. Roughly the same size and composition as Earth, Venus today is a vision of hell, crushing pressure, sulfuric acid clouds, and surface temperatures hot enough to melt lead. But this wasn't always the case. According to recent computer models, Venus may have had a temperate climate with liquid water oceans for up to 2 billion years. That's longer than it took life to evolve on Earth. It's entirely plausible that, in that deep window of habitability, life arose, and had time to grow complex. So what happened? Something triggered a runaway greenhouse effect. Volcanism may have flooded the atmosphere with carbon dioxide. Or perhaps something more deliberate occurred. If an intelligent species once thrived on Venus, could their own industrial activity have catalyzed the climate collapse? Did they burn through resources, ignite chemical feedback loops, and lose control? It would be the ultimate irony, a planet destroyed not by accident, but by civilization itself. Unlike Mars, Venus is almost impossible to explore. Its hostile conditions quickly destroy any landers sent there. The surface is obscured by thick clouds, making satellite imaging difficult. If a civilization had once built cities or machines, they'd be crushed, corroded, and buried beneath lava flows or kilometers of volcanic ash. The chance of recovery is near zero. But still, what if the planet's present condition is the afterlife of a technological age, not its beginning? This brings us back to Earth. If our sister planets may have once hosted civilizations, what does that say about the solar system itself? Perhaps it is not rare for intelligence to emerge, but rare for it to endure. Maybe the solar system is a graveyard of civilizations. Mars fell to cold. Venus to heat. Earth, for now, remains balanced. But for how long? And what if there was communication or connection between these worlds in the deep past? From a more scientific standpoint, exploring Mars and Venus for technosignatures, anomalous isotopes, structured formations, or traces of exotic materials, could be key. Already, projects like SETI look outward. But some scientists are beginning to argue that we should turn some of our attention inward, to our own solar system. Mars, Venus, even the moons of Jupiter and Saturn, any of them could hold clues to a forgotten chapter of intelligent life. And if we ever do find something, an artifact, an anomaly, a signal, it may reshape not only how we see Mars or Venus, but how we see ourselves. We will no longer be a solitary spark of intelligence in the void. We will be the latest in a lineage of cosmic stories that once burned brightly across the solar system. And Earth, then, will not be unique. It will be a survivor. Imagine, for a moment, that humanity vanishes tomorrow, not with a bang, but slowly, over decades or centuries. Our cities fall silent. Our machines rust. The satellites circling Earth continue for a while, then flicker out one by one. Nature reclaims our roads and buildings. The forests grow thick, the oceans swell, and time moves on, indifferent. Now imagine 10 million years have passed. What would a future intelligence, perhaps another species evolved from octopuses, raccoons, or something we've never conceived, be able to find of us? What would they know about the civilization that once covered Earth in glass, steel, and digital fire? This is where the story becomes sobering, even eerie. Because despite our current technological power and massive global footprint, the evidence of our existence may not be as eternal as we assume. Most of the structures we've built, skyscrapers, highways, dams, bridges, are astonishing feats of engineering. But none are built to last even 100,000 years, let alone 10 million. Concrete crumbles. Steel oxidizes and rusts away. Glass weathers. Without maintenance, our cities begin to fall apart in just a few decades. After a few thousand years, nature consumes them. After a few million, plate tectonics and erosion erase them completely. The tallest buildings in the world could become nothing more than mineral dust, indistinguishable from natural sediments. What about monuments carved into rock, like Mount Rushmore or the pyramids? These could fare better, but not forever. Wind, rain, freeze-thaw cycles, and the shifting of tectonic plates are patient forces. They grind down even the most resilient stone. Over millions of years, even the pyramids would become little more than oddly shaped hills. Perhaps a few fragmented blocks would survive, but without context, they could be mistaken for curious geology. And what about our technology? Our electronics, plastic casings, and data centers are incredibly complex, but fragile. Books decay. Paper disappears. Hard drives corrode. Digital data, if not backed up and maintained, becomes unreadable within decades. Even so-called permanent storage, like DVDs or optical discs, won't withstand geologic time. A future civilization would have to stumble upon a perfectly sealed, preserved, and powered facility, an unlikely event, to even know our media existed. However, some clues might still survive in odd ways. Plastics, for one, could leave behind lasting molecular signatures. While they degrade at the surface, fragments of plastic, especially microplastics, are already settling into the sedimentary layers of oceans and lakes. These could fossilize over time and appear as strange chemical anomalies in future rock formations, something unlike anything found in purely natural systems. Future geologists might puzzle over these polymers, never quite sure what purpose they served or where they came from. Synthetic isotopes, created through nuclear testing and power generation, offer another hint. Elements like plutonium-244 and neptunium-237 don't occur naturally in Earth's crust. Their presence in specific geological layers could be a red flag that an industrial society once existed. Even if no machines or buildings remain, the isotopic fingerprint would be unmistakable, provided future researchers had the tools and knowledge to detect and interpret them. Then there's the fossil record, which may contain indirect evidence. We might not leave behind skeletons in the traditional sense, but bones buried in landfills or sealed in burial sites could, in rare cases, fossilize. Even more intriguingly, future paleontologists might notice the sudden disappearance of countless species and the explosive appearance of domesticated animals. The sharp ecological footprint of humanity, deforestation, monocultures, invasive species, would show up as a rapid, global disturbance layer. A spike in carbon levels. A bloom of methane. A layer of ash or soot. And then, a silence. That silence would mark the end of our civilization as seen through deep time. No more industrial pollutants. No more construction. Just the slow, patient rhythms of Earth returning to equilibrium. If future archaeologists did dig into this layer of disruption, what would they think? Would they interpret it as the rise and fall of an intelligent species? Or merely a strange geological hiccup, an unexplained warm period, perhaps tied to volcanism or asteroid impact? They might find no buildings, no writing, and no tools, just chemistry. If they did find remnants of us, say, a buried underground vault of tools or a lost probe on the moon, they would have to reconstruct an entire civilization from fragments. And like us staring at a shard of pottery or an indecipherable script from antiquity, they would ask, who are these beings? What did they believe? Why did they fall? It's entirely possible that the true story of our species would never be known, only guessed at through the lens of the surviving data. A few oddities in the rock. A discontinuity in carbon. A whisper in isotopes. Or maybe nothing at all. Because time is merciless, and Earth is efficient at burying its dead. This perspective forces us to confront a haunting truth: we may not even be remembered. Our entire legacy might vanish like mist. The internet, the satellites, the cities, all gone. What we build now, what we treasure, might be invisible to the future. Unless we deliberately craft our legacy for deep time, etching records into diamond, leaving messages on the moon, storing knowledge in the DNA of unkillable microbes, our civilization may pass into silence like so many before it. And then one day, millions of years later, something will rise again. It will look to the stars, it will wonder about its origins, and it might stumble on our faint, forgotten traces. And perhaps it will ask the very same question we are asking now: were we the first? The Fermi paradox is a haunting question born from cosmic curiosity. If intelligent life is common in the universe, where is everybody? It's a question about the stars, about silence on a galactic scale. But what happens when we turn that question inward? What if the real mystery isn't just why we haven't found alien civilizations, but why we haven't found evidence of past advanced civilizations on Earth itself? This is the essence of what we might call the Fermi paradox on Earth, and it flips the traditional mystery on its head. If the conditions for intelligent life and civilization could arise more than once on Earth, and perhaps even have, we're left with a perplexing silence. Not cosmic, but terrestrial. Not, where are they? But where were they? The Earth is ancient, 4.5 billion years old. Multicellular life has existed for over 600 million years. And yet, in all that vast time, we see no clear signs of intelligence until the rise of Homo sapiens just a few 100,000 years ago. For something as powerful and transformative as a civilization, that seems like a suspiciously late arrival. If it happened once, why not earlier? Here is where the paradox deepens. The Earth has been habitable for billions of years. There were epochs where warm climates, rich biodiversity, and complex ecosystems dominated the planet. These conditions could have seeded intelligent life multiple times. If so, then where is the evidence? Why haven't we found ancient cities, roads, machines, or even carvings dating back tens or hundreds of millions of years? The answer may lie in the harsh truth we've already explored: Earth erases. Plate tectonics is relentless. Every few 100 million years, the continents shift, mountains rise and fall, ocean floors are recycled. What isn't buried is weathered away. What doesn't fossilize decays. And time, the great cleanser, ensures that all but the rarest traces are lost. Civilizations may leave behind towering monuments for thousands of years, but not millions. In this light, the absence of evidence may not be evidence of absence. It may be the natural result of the brutal forces that govern our planet. But perhaps the deeper issue is where we've been looking, and how. When we search for ancient civilizations, we look at surface-level ruins, preserved manuscripts, or artifacts in known archaeological layers. We're digging into a very narrow window of time, the last 10,000 years at most. Anything before that enters prehistory. Anything older than a few million years lies in geologic strata we usually associate with fossils, not tools. There's a critical blind spot here. We don't have a methodical discipline dedicated to searching for deep-time technology. We look for fossils of organisms, but we haven't built a robust field of technofossil archaeology, one that seeks to identify signatures of industry, not biology. And even if such a field existed, what would it look for? We don't know what the technosignatures of a civilization from 100 million years ago would even look like. They may have used materials or energy systems unfamiliar to us. Their cities may have been in places now buried or eroded, on the ocean floor, beneath Antarctic ice, or in regions subducted by tectonic movement. Their artifacts may have chemically altered over time, leaving only unrecognizable residue. This silence, then, may be one of detection, not of presence. It's also possible that our expectations are anthropocentric. We assume other civilizations would follow similar technological paths: metal, electricity, combustion, digital systems. But what if earlier intelligences had different architectures? What if they used biology instead of machinery? What if they evolved intelligence but never civilization, no cities, no roads, but language, and art that left no physical mark? Or, chillingly, what if their time on Earth was brief? Perhaps a civilization arose, reached technological maturity, and self-destructed. A nuclear winter. A nanotech plague. A bioengineered virus. A climate collapse they couldn't reverse. If they only lasted a few thousand years, like us, there's every chance that time, erosion, and geology have since wiped them away completely. They may have burned bright and fast, leaving only the faintest geological shadow, carbon spikes, isotope anomalies, unexplained chemical traces. In this scenario, we are not the first flame, only the latest. So we must ask, why haven't we found them? Because we haven't looked properly. Because we haven't asked the right questions. Because we don't know what we're looking for. And because Earth is an expert at hiding her secrets. It's possible the Fermi paradox is not out there among the stars, but here, beneath our very feet. As we reach into the speculative depths of ancient civilizations and the secrets of deep time, it's important to ground our thoughts in what science currently understands, what we know, what we suspect, and where the mystery remains. While the idea of forgotten advanced species and prehistoric civilizations can ignite the imagination, science is, by its nature, cautious. It works through evidence, method, and repeated observation. So what does science actually say about the possibility that humans are not the first civilization to rise on Earth? To begin, there is no direct, confirmed evidence of a prior technological civilization on Earth. Archaeology, geology, and paleontology have uncovered an immense amount about Earth's past: ancient ecosystems, mass extinctions, evolutionary transitions, but nothing that definitively points to industrial activity or intelligent technology before humans. No metal structures, no mechanical artifacts, no unmistakable signs of cities buried in deep strata of the Earth. This does not mean the idea is impossible, just that it isn't proven. The Silurian Hypothesis, proposed by NASA scientist Gavin Schmidt and astrophysicist Adam Frank, is not a claim that such civilizations existed, but a scientific thought experiment asking, if a technologically advanced civilization had existed millions of years ago, would we be able to detect it today? Their answer? Not easily. Schmidt and Frank argue that most technological civilizations, if they exist, may be geologically short-lived. Our own industrial age has been around for only about 300 years. That's barely a blip in the rock record. And if industrial societies typically collapse or transform within a few thousand years, their traces could be incredibly faint, especially in deep time. What the Silurian hypothesis makes clear is that the geological record is not a perfect archive. It's selective. Most of what gets preserved is determined by conditions of sedimentation, fossilization, tectonics, and chance. Organic material decomposes. Metal corrodes. Stone erodes. Entire continents have vanished under the crust or into the sea. Earth is not a static museum, it is a dynamic, shifting system that grinds down the past. This leads to one of the more provocative points in the paper. Our civilization may already be leaving behind clues that future scientists could find, just not the ones we expect. Instead of buildings or computers, they might find chemical signatures, artificial isotopes from nuclear reactions, elevated levels of carbon or methane in the atmosphere, residues of plastics and synthetic compounds preserved in sediments. These are the technosignatures that could survive deep time. And if we can detect these in our own future rock layers, it raises the question, have we seen similar anomalies in older layers, and simply not recognized them for what they might be? This opens the door to re-examining certain past geological periods. For instance, the Paleocene-Eocene thermal maximum, a sudden global temperature spike 56 million years ago, has no universally agreed upon cause. Some scientists link it to volcanic activity, others to methane releases from seafloor clathrates. But it's also the kind of planetary signature we might expect from massive industrial carbon release. Schmidt and Frank are not suggesting this was caused by ancient industry, only that, if it had been, we might not be able to tell. That is the heart of the scientific uncertainty. Because science deals in probabilities and falsifiability, it doesn't claim past civilizations existed, but it doesn't fully rule out the possibility either. Especially not when considering the limits of what can survive across millions of years. The Silurian Hypothesis invites researchers to think more broadly, to develop new ways of detecting ancient technosignatures, and to reconsider what kind of evidence we should be looking for. Of course, this topic straddles a blurry line between science and speculation. Mainstream science is cautious about embracing ideas that lack direct empirical support. That's not skepticism for its own sake, it's a safeguard against drawing conclusions from incomplete or ambiguous data. The danger is always in interpreting noise as signal, or mistaking unusual natural phenomena for artificial ones. This is why scientists approach things like out-of-place artifacts or strange geological layers with healthy restraint. Without clear context and confirmation, alternative explanations are always more likely. Still, the scientific community recognizes that we don't know everything about Earth's past, and that humility is necessary when dealing with timelines that span hundreds of millions of years. The deeper we go into prehistory, the more fragmentary the record becomes. Fossils get rarer. Artifacts vanish. And the potential for missed stories grows. In fact, the Silurian Hypothesis has inspired new thinking in fields like planetary geology, astrobiology, and technosignature research. If we want to detect intelligent life on other planets, we must first learn what kind of traces our own civilization might leave behind over millions of years. Earth becomes a test case, a model for imagining lost worlds and ancient minds. So the current scientific consensus is this. There is no direct evidence of prehuman civilizations on Earth. The possibility cannot be entirely ruled out, especially given the incompleteness of the deep-time geological record. If such civilizations existed, their traces may be subtle and require new detection methods. The Silurian Hypothesis is not a theory of history, but a framework for investigation, an invitation to expand our thinking, both on Earth and beyond. It's science at its most profound and humble, not declaring certainty, but recognizing the limits of our knowledge. And in those limits lies wonder. We often gaze out into the cosmos, searching for signs of life beyond Earth. We tune our radio telescopes toward distant stars, scan exoplanets for hints of water or atmospheres, and send probes beyond the edge of our solar system, all in pursuit of one aching question: are we alone in the universe? But perhaps we've been asking the wrong question all along. What if the real mystery isn't out there among the stars, but buried beneath our own feet? The Earth is ancient. It has spun in darkness and light for over 4.5 billion years, nurturing oceans, volcanoes, forests, ice ages, and mass extinctions. Life has risen and fallen again and again. Species have come and gone by the billions. We, humans, with all our knowledge and machines, are only the latest chapter, just a flicker in the long memory of this world. So what if others came before us? What if consciousness once bloomed in forms unfamiliar, scaled, feathered, furred, aquatic, even biosynthetic? What if civilizations rose in ages so distant we can't imagine their sunrises, where the stars looked slightly different and the continents were scattered in alien shapes? What if cities flourished under tropical skies that no longer exist, powered by sources we've yet to understand, erased by time, tectonics, and tragedy? And what if the great silence we hear when we dig into the Earth's past is not because no one was ever there, but because they were there, and they did not last? Perhaps they collapsed under their own weight, as we might one day. Perhaps they chose to disappear, fading from the surface and living in forms that left no trace. Perhaps they transcended in ways we can't yet comprehend. Or perhaps they were simply unlucky, their light extinguished by a meteor, a volcano, a slow climate shift they didn't notice until it was too late. The deeper question isn't just, are we the first? It's this: what does it mean if we're not? If we are part of a lineage of civilizations, some known, most forgotten, then our place in history becomes both more beautiful and more fragile. We are not the beginning. We may not be the end. We are simply the stewards of this moment. And that changes everything. It means our technological achievements are not a singular miracle, but a repeating possibility. Intelligence may not be rare, but its endurance might be. Maybe the real challenge isn't to reach space, split atoms, or simulate thought, but to survive ourselves long enough for the stars to remember us. And maybe, just maybe, some echo of the past still lingers. A buried artifact. A strange isotope. A carved stone no one can explain. Maybe it's waiting to be found by a curious digger, a satellite scan, a quantum researcher. Something that will whisper, "You are not alone." Because in the end, the most profound question isn't, are we alone in the universe? It's, were we ever alone on Earth? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.